Striving for perfection. It's about continuous improvement. And research is that continuous improvement that works towards perfection. With this, a very cordial good morning to distinguished guests, respected dignitaries, and passionate researchers. I, Harshita Shrivastava, on behalf of the IIT Bhopal University, warmly welcome you all to the second International Conference on Nonlinear Analysis and Computational Techniques, organized by School of Sciences and Languages, IIT Bhopal University, Bhopal, India. I am very glad this year we are joined by many participants from various parts of the world. On behalf of ICNACT 2025 and IIT Bhopal University, I wish all of you a pleasant and a fruitful stay during your time in IIT Bhopal University and India. As we delve into the rich tapestry of mathematical thought, let us embrace the spirit of curiosity and rigor as we explore the myriad ways in which mathematics shapes and enriches our world. Today, we are truly graced by the presence of several eminent personalities whose distinguished contributions in academia and administration continue to inspire generations. Their presence not only elevates the stature of this conference, but also reinforces the research, collaboration, and knowledge sharing. We are indeed privileged to have among us a galaxy of dignitaries who have been instrumental in nurturing academic excellence and innovation. I would now like to welcome our esteemed guests who are with us today. I warmly welcome Dr. Kothri-Kalan, our respected registrar and co-patron. With immense pride and honor, I welcome our chief guest, Professor Kamal Rajpal, and I also welcome our convener of ICNACT 2025, Dr. Hemant Kalita. We are deeply honored by the presence of all our esteemed guests and thank for their support and participation. As a gesture of our gratitude and respect, I now invite our convener, Dr. Hemant Kalita, to extend floral welcomes to our dignitaries. Now, I would like to take this moment to invite our chief guest, Professor Kamal Rajpal, and kindly request our respected convener to extend a warm floral welcome as a token of appreciation. Thank you, sir. I request Hemant sir to welcome our co-patron, Dr. Kothri-Kalan, whose constant guidance and support have always been a pillar of strength. A huge round of applause for Registrar. Thank you, sir. Last but not the least, I request Ms. Pandan, our student organizing member, to welcome our convener, Dr. Hemant Kalita. To begin with the proceedings, I would now like to invite all the distinguished dignitaries to join us in the traditional lighting of the lamp, as it is customary in this part of the world to commence any auspicious occasion with divine blessings, as the light, the symbol of positive energy for our occasion. In keeping with the rich tradition and culture of India, let us begin the conference by inviting our esteemed dignitaries to do the honors. take their respective seats. This event would not have been possible without the support of our convener, Professor Hemanta Kaneta. I would now like to invite him for the welcome address.
Good morning, everyone. Respected dignitaries on the dais and off the dais, respected Chancellor, respected Vice President, respected MEP Madam, respected Group Sir, respected Register Sir, Dean Directors of all the schools, faculty colleagues, attendees, guests, I, Dr. Hemanta Kalita, convener of ICNACT 2025, welcome you all in the second international conference on nonlinear analysis and computational techniques, in short ICNACT 2025 at PIT Bhopal-Indore. Firstly, I would like to thank Professor Kamal Raj Bardarsani, NIT Bhopal, who accepted our invitation to be the chief guest in the inauguration functions of the conference. I would like to thank Professor Senia from Tokyo, Japan, Professor Jha from Nepal, Professor Sajid Songar, and all invited speakers, all the expert speakers from the reputed universities and institutes for taking their precious time out and making this event propose. I want to thank all Dean, Director, colleagues, scholars for being present here today. It has been a real honor and privilege to convene the conference ICNACT 2025. The conference in this year has brought together a tremendous and rich diversity of authors and speakers from internationally reputed universities and government universities to share ideas and new perspectives on a wide range of nonlinear analysis and computational techniques. The aim of ICNACT 2025 is to provide a platform for researchers, engineers, academics, and industrial professionals to present their recent research work and explore future trends and technologies. Again, it is my great pleasure and honor to welcome to an inspiring, educational and enjoyable program in the beautiful campus of PIT Bhopal University. I hope that you will find the conference informative and enjoyable and to make the pursuit establish future national and international research collaborations, and that you will have a great stay in PIT Bhopal University. Thank you very much.
Thank you, sir. This conference is held by School of Advanced Sciences and Languages of PIT Bhopal. This conference aims to provide information about nonlinear analysis and computational techniques. In the upcoming sessions, we will engage with a diverse array of topics such as control theory and applications, numerical analysis, and much more. It aims to share the recent progress in the field of mathematical analysis and to promote a fruitful collaboration between researchers in the field. Now I would like to invite Dr. Kiran Kumar Mehra to give a preface about the conference.
Good morning all, respected Register Sir, Chief Guest, dignitaries on the net and off the net, faculty colleagues and participants. The initial idea of the conference was suggested by the organizing secretary and dean of the school, Dr. Hemant Nasruddin, last year, along with one of the conveners, Dr. Hemant Kalita. The primary research topic of this conference, nonlinear analysis and its applications in various areas with control theory, dynamic equations, ecological modeling, computational fluid dynamics, and optimization techniques. We are focused on the computational techniques that are used to approach the problems in these areas. We are fortunate enough to be associated with many publishing houses. So last year, for the conference last year, we were associated with Springer and Dignitary proceedings. They are published online this year. In addition, we are able to publish journals in our papers in journals like Mathematical Notes, Journal of Linear Analysis, Journal of Linear and Convex Analysis. Till date, we published around 60 papers on our conference last year. This year, too, our publication partners include Proceedings in Springer and Refreshment. In addition, we are with Associated Journal of Linear and Non-Linear Analysis, Journal of Nonlinear and Convex Analysis, and Paris Journal of Mathematics. We have received around 195 abstracts for this conference, after which we selected 90 abstracts. Dr. Hemant Nashine and Dr. Saurabh Mori oversaw the abstract review. The full-length paper, once available, will be communicated to the journals and will undergo the journal review process. Further, we have among us 15 invited speakers who will be delivering expert talks over the next 2 years. I conclude by expressing my gratitude to the management of VIT and management of VIT Bhopal for its continued support and trust in the conference. I hope this conference will be as successful like last year, and this will encourage us to organize the third edition next year. Thank you.
Thank you, sir. Our Registrar Dr. K.K. Nayan holds MSW and LLM degrees along with a 36-year-old long career in Bhel as the Zonal Manager at Bhel Head Office, New Delhi. Before that, he had served Bhel Bhopal, a large manufacturing unit in various capacities in the different functional areas of its human resource management. Dr. Nayan has a wealth of experience in both industry and academia. I would now request our co-patron and registrar, Dr. K.K. Nayan, to enlighten us with his thoughts.
Good morning. The respected Chief Guest of today's inaugural session, Professor Kamalraj Pardasami from MANIT Bhopal, Pro-Vice Chancellor, VIT Bhopal, the distinguished deans, professors, other faculty members, research students, and enthusiasts of this conference. I warmly welcome you all to this session. Second International Conference on Nonlinear Analysis and Computational Techniques. VIT Bhopal is extremely delighted to host this conference. We are 7 years old and going to be in the 8th year, and we are extremely delighted at the series of international conferences or conferences of national importance being held here. As a host, we feel extremely credit that in such competitive times we are able to hold and host such conferences in a meaningful manner. About the subject of nonlinear analysis, I have not much to contribute, except that in my undergraduate studies I was a student of mathematics also. And calculus was not one of my favorite subjects. So I don't venture into this, but one thing that is very prominent is that today's world is non-linear. It's not linear. Also, even we may wish it would be. When an Indian astronaut was to go to the space, we have seen how many times it got postponed. So it shows how the things are. So linear analysis would not be meaningless, particularly when it comes to today's world is described as you work by uncertain, complex, and ambiguous. Sometimes the relevance of the topic is very much up to date, and I hope this conference turns out meaningful and goes in a certain way or gives some leads on what needs to be done or how to tackle the issues, complex issues. It is what we call a linear world, as I said. The situations are becoming more and more complex, and it would require complex mathematical analysis to do it. So, I wish this conference the very best and the most meaningful interactions on the subject with experts from far and wide across the world contributing to it in a very, very meaningful way. I wish the conference all the success. Thank you. Thank you very much.
Thank you, sir. Now I would like to invite Dr. Dondu Anushka to give a brief introduction about our chief guest.
Good morning, everyone. I am Dr. Anushka. I feel very happy and honored to be our chief guest today. It is our great honor and feeling to welcome Dr. Personally, with academic researcher, our chief guest. Dr. Personally currently serving as a professor of mathematics in Maulana Azad National Institute of Technology. Post PhD in mathematics along with MSc in mathematics, which a rich background in both theoretical and applied domains, has great significant contribution to the field of computational, mathematics, computer application, and mathematical and computational biology. This interdisciplinary work spans across computational thermal biology, computational neurosciences, cell biology, biomathematics, and bioinformatics. He has 3,846 citations throughout his career, along with 8 different patents and 37 years of teaching experience. Beyond his research, Dr. Parsani is known for his dedication to academic excellence and mentorship. His vast knowledge and visionary insights continue to inspire students, scholars, and fellow researchers alike. We are deeply honored by his presence and eagerly look forward to his address, which will undoubtedly enrich the proceedings of this conference. So I kindly request Dr. K. R. Parsani to welcome forward and say two words. Thank you, sir.
Good morning to all of you. Respected dignitaries of all the dais and respected dignitaries of the dais, respected Dr. K. Nair, Registrar of the Bhopal, respected Dr. Keynote convener of this conference, Dr. Saurabh Warrior and Dr. Kiran Kumar Behra, conveners of this conference, Dr. Hemant Dashine, organizing secretary and chairman of this conference, all learned deans, professors, and faculty members of VIT Bhopal, and all participants of this conference. It's really a great honor to be here in this glorious institute of the region, VIT Bhopal, which I have seen growing stone by stone in last 7 years under the dynamic leadership of various management people, and I am surprised at the growth, the way this institute has grown in this region, because there are many other institutions in our region, and I couldn't find such a vibrant environment which has been developed in this institute, in all those institutes around this region. So it's really an honor to be here, and I thank the organizers for inviting me in this conference. The conference topic consists of two things, which are most relevant for the today's needs. One is nonlinear analysis, and second is computational techniques. So every phenomena in the world is highly nonlinear, not only nonlinear, but is highly nonlinear. And let us say control systems. The control systems are very sophisticated systems representing nonlinear phenomena, and till today we do not have sufficient mathematical techniques to perform the analysis of such systems. And the second thing is the computation techniques. So that is the basic tool which is required to solve the world problems which have been formulated mathematically. So mathematical formulation of real world problems lead to nonlinear models, and to solve these nonlinear models we need computation techniques. So we need various analytical and numerical or computational techniques for analyzing these. So this topic of nonlinear analysis and computation techniques is highly relevant for today's research in every field, almost every field. Now, it's a great challenge for the mathematicians to understand the nonlinear systems, and that leads to development of further mathematics. So this is what it is a two-way feedback system. You have problems of the world which are nonlinear. You perform their mathematical modeling, and then you develop mathematical techniques to analyze them. So you are giving to the world your solutions. At the same time, you are getting the challenges from the world to develop your own mathematical techniques. So this topic, combination, nonlinear analysis and computation techniques, are very good combination, which is the basic for all researchers. And we will see from the list that there is a lineup of very good international speakers And also the participants which I am observing here, sitting here, and many maybe online, mostly look to be very mature. And because what I find is, I attended so many conferences, and I find people come to the conference and it's just like a meal. You have large number of people moving here and there, and the organizers of the conference, they have provided you the platform to share the knowledge. Learn something from the conference. Once I visited two conferences, and my scholars were with me. So we attended both the conferences. I asked my scholar that you give me 5 different learnings which you got from the conference. And then they came out after the conference. Then I asked them which was a better conference. So one was held in a local engineering college, it was the Bhopal-Indore college, and another was in a central university. In that local, the number of participants were less. In a central university, participants were large, but the students said the conference which was held in local was better. I said, why? He said the participants as well as mainly the speakers were better in this conference. So the conference is for the participants and by the participants. If you really get involved in the conference, in academic deliberations, you will really learn out of it, and that is the purpose of the conference, that every participant carries something with some weight with them. So this conference, I say that it will be a grand success if really the participants sincerely get involved and they are able to derive out something, some new learning, some unique learning, which can be useful to them for their research, future research, and they can contribute into that. And even the learning can help you to come out with some unique solution to your problem you may have learned from somebody else or your participant. So I believe that participants will sincerely participate, get involved in discussions, and try to pick up good knowledge, good information which can be helpful to them. The conveners, the organizers of this conference, they have made very nice efforts to organize this conference, providing a platform for sharing knowledge, and I'm sure this conference will have very happy deliberations, and all the participants will enjoy the deliberations of the conference. And I wish this conference a grand success. Thank you very much.
Thank you, sir. It was really insightful. We are truly honored by the presence of our distinguished dignitaries whose gracious presence has made this event more special. As a token of sincere appreciation and respect, I request our convener, Dr. Himanta, to felicitate our chief guest with a token of appreciation. A huge round of applause for our chief guest. Thank you, sir. Now I would like to request our respected chief guests and other dignitaries to release the souvenir of our conference. Thank you, sir. I would now like to invite Ashish Sani to deliver the vote of thanks.
A very good morning to all of you. It is both an honor and privilege for me, Dr. Ashish Kumar Kesavani, on behalf of the organizing committee of ICNACT 2025, to deliver the vote of thanks for this vibrant and intellectually enriching conference. First and foremost, we are deeply grateful to the leadership of BIT Bhopal University, especially patron Honorable Dr. G. Viswanathan, founder and chancellor BIT University, our patron Mr. Shankar Viswanathan, Vice President BIT Bhopal University, and Ms. Radhandri S. Viswanathan, Assistant Vice President BIT Bhopal University, for their constant encouragement and support. My sincere gratitude goes to our co-patrons, Professor T.V. Siddhidaran, Professor BIT Bhopal University, and Mr. K.K. Nayak, Registrar BIT Bhopal University. Thank you, sir. For their unwavering guidance, even with their tight schedules, they remain readily available whenever we sought their support. I would like to extend our heartfelt gratitude to our chief guest, Professor K.R. Pardasni, for gracing us with his presence and for sharing his invaluable insights during the inaugural session. Sir, your vision, encouragement, and words of wisdom have truly inspired us all and added great value to this event. Thank you, sir. Thank you very much. I also extend sincere thanks to our distinguished across the globe who will share their expertise on the diverse range of topics from non-linear analysis to real-world computational techniques. Your contribution will not only enrich our knowledge, but will also spark new ideas and research directions. It's a note of appreciation to our chairman and organizing secretary, Professor Hemant Kumar Nasine, for his unwavering leadership, and to the conveners, Dr. Hemanta Kalindar, Dr. Saurabh Kumar Maurya, and Dr. Kiran Kumar Behra, for their meticulous planning and coordination. I would also like to acknowledge my fellow organizing committee members, Dr. Anupam Singh, Dr. Sanjay Ram, and Dr. Dotu Harish Babu, for their teamwork, dedication, and effort that made this hybrid conference run so smoothly. I would also like to thank all the dean, directors, research scholars, and media faculty colleagues for your support and encouragement. To all the participants, presenters, researchers, and students, thank you in advance for your enthusiastic involvement and for contributing to the rich discussion and collaborations that will take place over upcoming 2 days. Last but not the least, our heartfelt thanks to the facility team led by Mr. Murugan, administrative staff, and student volunteers who work tirelessly behind the scenes. We appreciate your hard work, dedication, and energy. ICNACT 2025 will be a grand success because of every one of you. We hope to continue this academic journey together in the years to come. Thank you and Jai Hind.
Thank you, sir. Thank you all for your attention and participation during this inaugural session. We have had some insightful discussions and valuable insights shared by distinguished speakers. I wish you all an inspiring and fruitful conference. May your discussions and collaborations pave the way for future breakthroughs and innovations. We will now take a short refreshment. Refreshments are available at 84.5, and we encourage you to take this time to relax, network, and connect. Our next session will begin promptly at 11 a.m. Please make sure to be back in your seats by then so we can continue with our take this opportunity to connect with our attendees and enjoy our refreshments. Thank you once again, and we will see you shortly. appreciate your prompt return as we continue with this a lineup of distinguished speakers who will share their insights on their subjects. So, to ensure the smooth running of our sessions and to guide us through the discussions and presentations, we have an esteemed session chair. It is my pleasure to introduce our session chair for this session, Dr. Zahir Karim Ansari, who is a doctorate in mathematics from Dr. Hari Singh Kaur, University Sagar, having an academic and administrative experience of more than 30 years. He has worked at various levels up to professor, head of the department, and first-year coordinator. He has 45 plus publications in peer-reviewed international and national journals and conferences. He is a life member of Indian Mathematical Society and his area of research is point theory. Please join me in welcoming Dr. Zahir Karim Ansari.
Thank you, Madam. Once again, welcome you all for Second International Conference on Analysis and Computational Techniques. In this session, we have 3 invited talks and 4 or 5 presentations. And since we have a little shortage of time, so I request each speakers to please contain your contents on time. So in this first talk, I request Professor Kamal Raj Pradarshini. His introduction always given by during the welcome address and inauguration. And such topic is modeling neural chemical signaling system dynamics. And we all know that sir is working in IIT Bhopal and having a vast experience just talking to him and he experienced talk about various places he has worked. So sir, please insight, give your starting talks to us. Thank you. Professor Pradarshini.
So thank you, Dr. Ansari, for inviting me and introducing me here. So friends, as the conference topic is computational techniques and nonlinear analysis, so this is one of the topics which fits in that area. And you will find the computational models here, as well as the dynamics, nonlinear dynamics is involved in this phenomenon. How we analyze that. Next. So our brain consists of various neuron cells, and the size of neuron cells is few microns. And this small cell has a beautiful control system. That is what we are wanting here. The whole communication with the nervous system takes place through these nerve cells, which are of different types. One of them is neurons. And this communication takes place by 2 ways. One is the electrical signaling and second is chemical signaling. So today I am going to focus on chemical signaling, and there are various chemical ions which carry the signal, and one of them is calcium. So all chemical ions are known as second messengers, and electrical signaling is a first messenger. The second messenger is chemical ions. Now there are regions where the gap is more than 10 microns. There the electrical signal cannot pass. When the gap is more than 10 microns, the electrical signal cannot pass, and therefore the chemical signaling starts working there. So the electrical signal is converted into chemical signal, and So where there is a gap, the positive charge activates the calcium, it repulses the calcium, and then calcium is positively charged ion. It carries to the other end and it gives its charge to the other end. And from there the signal, electrical signaling is continued. So calcium is an important ion. The second aspect of calcium is that free calcium is harmful to the cell. In the body, there are 99 uses of calcium, and whatever calcium is stored in the cells, we use only 1% of that calcium, and that calcium is also free calcium for longer periods is harmful to the cell. It causes cell death. So, whenever any activity is to be initiated, the free calcium concentration is increased. Whenever activity is to be sustained, the free calcium concentration is increased. And when the activity is to be terminated, again the free calcium concentration is to be increased. So these are the three different signals. So it has to be increased for that activity, and once the activity is over, calcium will be flushed out of the cell to the store. There is a separate store for calcium. There are some internal stores and external stores. And how calcium is stored? Calcium is combined with some proteins which are known as buffers. And there are 50 known buffers. They are proteins which bind the calcium, and the bound calcium is not harmful to the cell. So whenever the calcium is required, the dissociation of calcium from the buffer takes place, and it increases the calcium concentration in the cell. So all the activities, cellular functions like secretion, fertilization, gene expression, muscle contraction, they are based on this signal. And every process, heartbeat, muscle contraction, bone activity, brain functionality, is based on the calcium signaling. And if this calcium signaling fails, it leads to neuronal disorders. So we need to understand the importance of this area. We need to understand this whole process. So calcium is maintained at 0.1 micromoles when the cell is at rest. And this concentration can be increased up to 10 to 50 micromoles. And once the job is over, the concentration will come down to 0.1. Cell comes to the rest. So this is the whole control process. Now there is some internal store known as endoplasmic reticulum (ER), which is the internal store where free calcium is stored. There it's not harmful. Then calcium is outside the cell also. There are certain stored, and there is another molecule called IP3, cytosol triphosphate. So how the internal store is opened? So there is agonist which comes at the cell, and that agonist releases IP3 molecules, and IP3 molecule comes to the internal store. It opens the gate of the internal store, and the free calcium comes into the cell. And again, when the work is over, the same IP3 molecule will combine with calcium and block the gate, and then it will open the other gates from which the free calcium will be put into the internal store, or there are gates from which the calcium has to be thrown outside the cell. So this is the whole process which takes place. So IP3 is another molecule which is of importance. Then there are other molecules like beta amyloid, adenosine triphosphate, nitric oxide, dopamine. These are the hormones, some of them are, these are more hormones, DA and beta amyloid are hormones which are used by the brain for various activities. So again, these in the required quantity, there is certain required quantity. If they are there in that required quantity, it's okay. If there is shortage of this, it will lead to neuronal disorder. If they are in excess, again they will also cause cell death. So their excess and their shortage both is bad for the cell. So it's a complete regulation. Now the challenge here, these chemical molecules, they also depend on calcium. Calcium all, and they all depend on calcium and ITP, as well as calcium and ITP concentration also depends on this. So we have a system of signaling systems. We have a system of signaling systems in the neuron cell. So signaling systems have been studied independently in the neuron cells, like calcium signaling, IP3 signaling, beta amyloid signaling. They have been studied independently in the past, but they also regulate each other. So all those studies are not realistic. To make them more realistic, is there's need to integrate these signaling systems and then study how they are regulating each other. This is a whole highly nonlinear control phenomenon, and we do not have sufficient mathematics to understand this phenomenon. But whatever tools we have at present, we try to analyze it for that. So next, so the associated signaling molecules here are beta amyloid. They are indicator of neurological illness, and let's say shortage of this will cause ischemia and excess will cause Alzheimer's. Then this nitric dopamine, it causes Parkinson's disease. There are other neurological disorders which are caused by ATP and nitric oxide also. So we have basically focused on ischemia, Alzheimer's, and Parkinson's in our studies, and other studies also can be done with the help of these. So interaction among these signaling systems is a challenge for modeling, understanding the nonlinear behavior, and using computational techniques to solve that. So this I already explained. IP3 receptors are there where they open the gate of the internal store. There is a circuit pump from where you can remove the extra calcium into the internal store called ER, endoplasmic reticulum. And then buffers are there. There are 50 different types of proteins which act as buffer. They combine with free calcium to lower the calcium concentration in the cell. Free calcium concentration in the cell. So these are the mechanisms which are involved, and with this theory, we perform the mathematical foundation of the problem. So we consider these equations here. So we have the first equation, which was given by Wagner et al. In 2004. This is a calcium rate of change of calcium with respect to time. This is a diffusion term, and these are the various terms due to different organs like IP3R. So interaction of calcium with IP3R leads to some generation of calcium or reduction of calcium. Then some calcium is removed from the cell by circuit pump. Some calcium leaks from the internal store into the cell. Then there are some random receptors which facilitate the influx of the calcium into the cells from outside, and this is beta amyloid. So beta amyloid also causes some calcium to get into the cells, or it leads to some production or absorption of calcium. So that is the reason term here. And then this is the amount of calcium which is reduced or increased due to buffering activity, buffer. the buffer will either dissociate the calcium to give free calcium, or it will bind the calcium to reduce the free calcium. So this is the term. Then you have IP3, same diffusion term for IP3, production of IP3, and there is some process by which IP3 degradation takes place. There are two processes, kinase and phosphatase. By that, the degradation of IP3 takes place, and this gives you the second equation again given by Wagner in 2004. Now, these equations were studied independently earlier, and we have tried here to combine these two systems, three systems here. This is beta amyloid. DuPont gave this equation in this, here is the diffusion term of beta amyloid, there is production term and degradation term. So, beta amyloid also depends on calcium, and calcium depends on beta amyloid production. So, production both depend on each other, degradation of both depend on each other. So, in this way, the equations depend on each other. So, these are the various terms given by various authors. We use these terms again, these mathematical expressions taken from these references, and you can see this, they are depending IP3 and calcium depending each other, and production also depends on various molecules here. So I'll come to this. So this is the formulation we have got here. Then we have some initial and boundary conditions to be formulated. And they are formulated using the physical conditions of the problem. So we know that calcium at rest is maintained at 0.1 micromoles when cell is at rest. So time t equal to 0 cell is at rest. IP3 concentration and the cell is at rest is 0.16 micromoles. Amyloid beta is 0.00 micromoles, 0 micromoles when it is at rest. And then we have the flux conditions here. They are dependent on various physical conditions. We take the values from there, and this is the influx of calcium from outside to various input channels are there, then at another boundary the calcium is maintained at 0.1 micromoles. So these are the boundary conditions. Same way we have the boundary condition for IP3 and same way for beta amyloid. Now we come to another formulation of neuronal signaling of calcium, IP3 and nitric oxide. Same way we formulate the problem. So the first equation of calcium is same, only one term will be changing, that is which depends on nitric oxide. And here nitric oxide production and degradation, that depends on calcium. And then there is IP3 equation. Again, this is the same equation which we have taken from here, but this is again depending on DA, dopamine here. This is for dopamine. Okay. This another one. This is for dopamine. So dopamine IP3 depends on dopamine also, and dopamine depends on IP3 also. So this is the way we are coupling the equations here. So this is the third problem which we form for we found the synergy among the three signaling systems: calcium, IP3, and dopamine. And this we have formulated for study of Parkinson's disease basically. So I'll come to the methodology of research work. So we make use of finite technique. I'll not discuss the whole procedure of finite element here due to shortage of time, and therefore we get the system of ordinary differential equations here. This is something wrong. It should not be del. It should be d. D u bar by dt like this. So we get a system of ordinary differential equations, and we use Crank-Nicolson method to solve this system of ordinary differential equations. And why we use Crank-Nicolson method? Because it is unconditionally stable. Because stability is another problem when we use computational techniques. So I'll come to the results and discussion. You can see here the neuron cells, we get the results here. How it is varying when it is normal neuron and how it is varying when it is ischemic neuron. So ischemic condition and normal condition, we are getting this these gaps, due to in the calcium profile as well as IP3 profiles also. Then this is for beta amyloid. Under external conditions, what is the difference among these? So a minor difference in beta amyloid formation causes a significant difference in calcium profiles. You can observe from here. No problem. Basically, conservation problem. Yeah, I was on this slide. So you can see the difference in the results. I've not put all the results here, just to show you. You can see the differences again in the profiles here for different profiles when property of the gate. P0 is the property of the gate open. How much gate is open? This gate is closed. Gate is 50% open. Gate is 100% open. What is the change in the profile level? You can see the difference in the profiles. There is a lot of gap among them. And this you can see the non-linear nature of these profiles here. How the lower profile is there and how the nature of the profile is changing with the conditions. You can see from here. So this shows that there is quite significant effect. Again, you can see here when IP3 receptor is inactive, you have the profile. When IP3 receptor is active, the profile is different. So when it is inactive, it is almost linear. When it is active, then it becomes non-linear, and there is quite a big gap. Now these are the results showing difference in calcium and IP3 concentration at various times. So the difference in the calcium and IP3 concentration, that difference quite it is increasing as you go from the surface to the inside the cell. That's also increasing here. So concluding remarks here. These models which we developed, they are superior to the existing ones where the single systems were studied independently without incorporating their dependence on other signaling systems. And we observe that when you take the dependence, incorporate the dependence of signaling systems on each other, the results are totally different here. So next, we come to a two-dimensional model here of two interdependent systems. Now, this what we proposed was a more realistic model than the earlier ones, where we were able to incorporate the non-homogeneity of the medium. So, this is an equation in two dimensions, same equations which we took up for the previous problems. So these equations are in two dimensions here. And these are the boundary conditions for those equations, same boundary conditions here, which we took there. And then here we are incorporating additional terms which are called as mitochondria. Mitochondria is another internal store. One is ER, ER is endoplasmic reticulum. That is one internal store. Second internal store is mitochondria. And there is a connection between ER and mitochondria. That is called MAM. That is mitochondrial associated fluxes in neuron. So, these terms we have incorporated here, and we get these three systems, separate systems for each. So for ER, the equation is separate. For mitochondria, the equation is separate, and for MAM, the equation is separate, and for status of the cell, the equation is separate. But all four equations, they represent what? Calcium signaling on. So calcium signaling is different in different compartments, what I would like to say here. That is what we are incorporating in this model. And then again we have IP3 also in different compartments and different equations. So we got some 6 equations here. I'll show you the figure here. This is the 2-dimensional figure of the cell. We divide this cell into number of elements depending upon our requirements. And this is the situation. You have an ER and connection between mitochondria as MAM and mitochondria separate, and then the cytosol, the surrounding area is cytosol of the cell. So, discretizing this region into this, we follow the finite element procedure and we get the system of equations here. And then we can see in the results, one is the changes occurring due to non-homogeneity of the region. Is composite media, and for different compartments, IP3, leak, RYR, for different compartments, the calcium concentrations levels are different. You can see from here in both the dimensions. These are looking like islands here on this land. So this clearly gives a picture about how the concentration is changing. Now for different source inflows, by the color code you can see the level of concentration changing with respect to the non-homogeneous conditions of the region along both x and y directions. This is another kind of non-homogeneity which was observed for if the buffers are of different kinds. I said there are 50 different types of buffers. So we took 4 different types of buffers: S100B, EGTA, calmodulin, palmidin, and calmodulin. So these buffers, the last one buffer is a fast buffer, and those buffers are slow buffers. So you see the concentration level where buffers are slow is high, and the concentration where buffers are fast is low. So you see the level, how the level of this concentration changing if the buffers are non-homogeneously distributed in the cell. This again the system of mitochondria and cytosol and ER. In all 4 different compartments, the calcium concentrations are found to be different at different points of time. Again, this is showing the similar result. So, concluding remarks that the finite element technique is quite powerful and versatile to handle such situations, and we have already seen from the results that it's able to give you the clear picture of all the changes which are cellular level in calcium or IP3 or ED or PD, whatever it is. So, any dysregulation in this system, it can lead to neurological disorders like Alzheimer's, Parkinson's disease, and so on. Now, We have also performed the error analysis presented in the slides. And the second thing is stability analysis. Both the things we have done. Our system is completely stable because the eigenvalues are all negative and value of lambda is less than 1. And errors were computed, absolute errors were computed by increasing the number of elements. After a point, if you increase the number of elements, the error is negligible. So we stop there and we take that number of elements in the model. So these are two things we did, and with the help of this, so now there's a lot of scope for further research in this area. You can combine more signaling systems, incorporate their effects, and see how disturbance in one signal to disturbance in another signaling system. So earlier what we are doing, we were trying to study one signaling system, and we were saying that if there is any disturbance in calcium signaling, it will lead to this disease. But from where that disturbance has come? So there is another system in which some abnormalities is there or signal disturbance is there, which is being conveyed to calcium, and then we see that calcium is abnormal. But where the root lies? So we are not able to identify by studying one signal system that what is the cause. But the root cause is somewhere in another signaling system. So if we equation of all the signaling systems, and then we see that if there is a problem in one signaling system, how it is going to affect signaling systems on the long time, how it can lead to that disorder, neuronal disorder. So that's what is the future scope, and you can consider many different types of buffers. We consider only 4 types here. There are 50 types. Then you can extend it to the 3 dimensions to make it more realistic, and more internal stores are there. Like Golgi bodies, etc., they can also be incorporated into this model to improve this model. And and then we can consider all those conditions which are leading to this dystonia, Alzheimer, and Parkinson's disease. It can lead to identification of this. This is a list of publications. This work was done by Dr. Anand Pawar. Now he is working as assistant professor at MIT Bhopal. Last year only he has completed PhD, and he has published all his papers in SCI index journals from this thesis. All you can see this boy. He worked very hard. He used to come at 8 in the morning and go back at 8 in the night. And he has given me the largest number of essay publications from his thesis up till now. You can see this again. All SCI 10, 13, 16, 19. He has published 19 SCI public papers in the last 4 years. You can see from here, from 22 to 25. And these are the references which we have used in our work. And if you have any questions, you are most welcome. Thank you.
Any questions?
Yes. Initial boundary conditions are determined. In this area, a lot of experiments are going on. There are laboratories also. So they have the physical conditions, and those are reported in the research papers also. So we pick up those physical conditions, and then we develop the model. So in the experiments also, what they do, they inactivate one organ also. They think that this quantity, this organ will be inactive. They put some chemical into that, so that organ will be inactive. The other organs will work. So what is the effect of both organs? So they are doing it experimentally. Now experiments take a lot of time actually, and modeling certainly you can get the results in faster mode and it's very economic and feasible, whereas many times practical experiments are not feasible. So it's better to go for mathematical models. So once you have those input data from there, you can develop the physical conditions. Here. Okay, thank you.
Thank you for your insightful thought. Calcium generally we thought is used for bones to strengthen the bone. Now here sir had given the insight that is they disturb the neurons also and giving the two very important diseases Alzheimer and ischemia. So we have to be careful in Bhopal itself because the exact Bhopal water having less calcium. So please eat banana. Thank you sir for your thoughtful sir. Thank you.
Now I request the session chair, Said sir, to facilitate Kamalraj sir with a token of appreciation. Now we have technical sessions with Professor Zaid Khalid sir.
Thank you. Our second today's talk is given by Professor Mohammad Sajid, and Professor Sajid is currently working in the professor in the IIT, sorry, Qasim Mechanical Engineering, Qasim University, Saudi Arabia. So he has did his PhD from IIT Kanpur, and since time is less, therefore I'm not going in detail. The topic of talk is fractal and cross in difference and differential equation with application. So please give your talk. Please, I request those who having your slide or presentation, please send to ID. Conference ID, that is ICAT at the rate of .ac.in. Please. After this is Professor Kanhaiya Lal. Please, if you don't have, to please send to this, and followed by Rachel Sara Di Costa. Please send if you have not sent it. Then Arga Ghosh. Then Rushelvet. And followed by Mirikim Pemi. Please send your PPT.
Now I start my talk on fractals and chaotic difference and differential equation with application. So actually here we have taken difference and differential equations. Actually sometimes both are same when we apply the computational technique through computer. When we draw the pictures, mostly what we do when we have differential equation, mostly differential equation we are not able to directly draw. So what we do, we discretize. We do the discretization, then we get difference equation. So generally we solve the through computer in steps. We choose the steps, and in that way we will get mostly difference equations. So both almost same, but depends on the situation. Sometimes we use a difference equation, sometimes we use the differential equation. Okay. So now we go to next. So this is abstract of my talk. I think it is already given in my. It is given already in booklet abstract book. So I think don't need to repeat this again here. So just I start with this. Now we start with some pictures. Okay, beautiful picture. So in these pictures, we can see that these are the pictures. So some of them are natural pictures, some of them are mathematical, computational generated pictures through a computer. So first one we have generated this picture. It is a solution of differential equation, especially complex differential equation we have solved, and then we have found the solution. Then we apply the iteration technique, we will get this. Second one, we have directly applied the complex function, and we have generated this through discrete system that is related to difference equation. Third picture is this. It is like this broccoli. It is original broccoli picture. Okay, original photo. But it is a. We can see that when we go further step, we will find it is like a fractal. And last one also generated picture some mathematical formulas. So we will go next. But actually, what are now Mendel brought one of the mathematician, how we say scientist. So he also known as father of fractals. So he told that clouds are not spheres, mountains are cone, Coastline are not circle, bark is not smooth, nor does light in a straight line. So his idea about some problems around us. He told like this. So after that, these quotations are very success and published in many papers, and after that he recognized some more thing about this. What are these? So if things are not like that, so what are shapes of trees, mountain, and clouds? So if things are not like that, so what are the shapes? What are the names? Natural shape or mathematical shapes or scientific names? We must know, then we can study. Okay. So does line travel in a straight line? Why two pieces of broken teeth never be rejoined even though they appear to fit together at some gross scale? Or how big they are and how long they last? Sometimes we see a long distance looks small, okay, but they are big. Sometimes things are very small, we go inside, it's very small. So things like that, what we say. So further, they have developed a definition of fractals, and they told like this: fractal can be defined in terms of characterization, no hard and fast definition. Fractals are regular shapes, self-similarity, fine structure, house dog dimension is strictly greater than is topological. People are developing the definitions of fractals. Maybe in future, maybe more definitions or more things about fractals. So how to understand this definition? So serious. So if we go inside, if we cut like this, we zoom it, we can get a fractal like this, structure like this. We have another kind of structure. We have like this is also a fractal. And we have another kind of this picture. We go inside and inside and inside. So these type of picture are fractal. So Mendel told like that. If we have structure like this, these are the fractal. And his book very famous, Fractal Geometry of Nature or Geometry of Nature. So he has written many research papers like that, and all papers about these things successfully used by others and applied by others in industry and business and in other scientific calculations. Okay. So how to understand the fractal? So if we say simple fractal is this. If we take a candle, the simple, if we take a candle set, so what is the candle set? Everyone know about the candle set, but this candle set, after definition of Mendel, so he told that it is a one kind of fractal. So what is that? If we cut 1/3 and we get two lines. Again, follow up this structure, cut 1/3 and so break like this. So we continue this process, we get a fractal. This is one kind of fractal, and this fractal is just points, dust, like a dust. So this is called also sometimes fractal like a dust. But we can understand more about fractal if we think about another kind of fractal, that is coastline. If we take a line, and in this line, if we cut 1/3 and put two small lines, and continue this process, so we small line and we put two more lines and continue this process like this. So we get fractal like this. So this is the one kind of fractal, another kind of fractal. So we can see more example about that. That is called self-repeating triangle. This is another kind of fractal. So if we say that we take a triangle, we cut 1/4 triangle, each on the each black part, again cut 1/4, and finally we get a fractal that is called frequency triangle. So mostly named based on who has given this fractal and related to picture. So both. Next is frequency carpet. So what we are getting, have a square, cut 1/9 part and apply same thing, and we get a picture like a carpet, designed like a carpet. So they have given name like this. We can see another kind of fractal, that is a frequency cube. So we have a taking cube and cut inside, inside and inside, we get picture like this. So we have either simple line or plane, or we have three dimension. There is no issue, we can construct a fractal. Now we go to next, we can construct a fractal of any kind of function. It is a complex function. So just second, if we function, this function we can discretize. We choose point, and we do the iterations. So we can construct a fractals, and for this function, for different parameter A, B or C, we get a different kind of picture. We can choose different parameters and we get different pictures, and above pictures are Mandelbrot set, down picture are Julius set. These are the definition in complex plane. If you go for more detail, you can see the definition, and according to that you get a picture. through changing the R. So when we change the R, we get in the beginning fixed point. Then we get fixed point, but next is periodic point. Period 2, then period 4, then period 8, like that. So periodic cycle increasing, finally we get this dark region. This is a chaotic situation. So there are many theorems about that to show that this is a chaotic situation. Sometimes we get a periodicity. So this is a root of chaos. How to show this root of chaos as a chaotic behavior? So there are many mathematical formulas, there are theorems to show that this is a chaotic situation. So a lot of work has been happened on this simple polynomial. And many books written only for this simple function to show that chaotic. Okay, so we go to next is how to recognize the chaos. So we have this. So some sudden and changes in non-linear system may give rise to chaotic behavior called chaos. If system is non-linear, so more chances we get a chaos. Okay. Yes. So signature of chaos is divergence of nearby project. So we try to convert this theoretical thing in form of mathematical form. So divergence of nearby trajectory. It means we have a sequence. We want to show that one sequence is going this after some steps. This is a divergence of trajectories. Okay. So necessary condition for chaos. All chaotic system are non-linear, but not all non-linear system are chaotic. Okay. So now fractals are related to geometry, appear as delightful but infinitely complex shape on line in a plane or in a space. These are fractals. Notion of chaos is related to dynamics or behavior of physical system. It is a behavior. But fractals are geometrical things. So in the beginning of 21st century, number of advancement in science, engineering and technology has been happened due to leading research and development of late 20th century which can be associated to use of fractal and chaos. So now we go to things difference of differential equation. Just I try to connect with other things. Okay, so mostly these are related to dynamical system. Dynamical system also two types, linear and non-linear. Inside the non-linear, we can also categorize discrete and quantum. So mostly we try to find the chaos in this last one. Okay. So differential equation related to Schwarzschild derivative. So we define this Schwarzschild derivative, and this Schwarzschild we have certain condition. Then this differential second degree differential equation has this solution f z equal to z e1 and e2. So I try to find a fractal for this f. So we have taken this Schwarzschild function and Schwarzschild derivative of this function is this, and we have tried to find the f solution, and then this solution, and we find the fractal for this for different value of lambda 0 to 4, 4 to exponential 3. So we try to generate a fractals like this for different value of lambda equal to 3.9, lambda equal to 4.1. So see that for different value of lambda, these are different fractals, but change at 4, big difference. So this is the chaotic behavior. So both things here. Now we have more fractals here. So we have dynamical system equation like this. Any kind of dynamical system, non-linear dynamical system. So a lot of dynamical system, you see that this is the differential equation, and this is the discrete system. Okay. So this system we say that difference equation. Okay. This coming from difference. Okay. So we can see that differential equation, another kind of differential equation, Lorentz model. Three differential equation gives this type of chaotic behavior, and this is a fractal. And now this is the Diller model. So these are also pure have a chaotic solution. Diller logistic loss model. These are difference. We can use a difference equation. We can generate this chaotic behavior. We can see. In our model, we have these equations. We can get this type of chaotic attractor. So we can see more. These are rotation. We will generate a two-dimensional system and we take a rotation map and we get this kind of pattern. So we get a solution like this. This is the basic output. We can say this the local convergence analysis are two iterative methods. So we use these equations, recurrence equation, and we find these different kind of. And also we can see that the dynamics of a generalized Lorentz-like chaotic dynamical system. So Lorentz system changed by some different adding some parameter, and then we find different type of chaotic behavior and also disaster. System of three different equations. This is very interesting. Three equations. When we use a parameter, we get C shell type of picture. So this is one kind of factor. Because inside that, many kind of symmetry we have, many kind of self-similarity or different kind of many things we can satisfy. So if there is some chaotic certain parameter, we have a chaotic form like C. Okay. And we have some different kind of data pre-modeling, study the dynamical system. So we have this type of chaotic attractors. Rochelle model, we have different kind of differential equations. So we get this is very famous Rochelle model, and we have different type of attractor and chaotic path is there. And this is another kind of model. And this is a stability bifurcation, pure control of discrete time greater model. So we have this. So we see that take a different parameters, we get different kind of features. Okay. So we have another kind of things. This is a used in a fluid duplex system. So inside that we try to generate a picture of this. It is a looks like a periodic doubling and we get a like a structure like a fractal. So we can see that found there is a region of large force maybe exhibit the chaotic motion of duplex. So Lyapunov experiment is one of the things. Sometimes we can use to say that system is chaotic. Always will not work for all system. This will not work. There are many more definitions about depends on system. We have to show that system is chaotic. But sometimes easy definition is this, very easy and most useful definition. But sometimes it will fail this definition. We have many more definitions to show that system is chaotic. I show one is greater than 0. So this lambda is positive, so we say. So this will work for not for our system, but most of system this will work. So now with 3D fractional order chaotic system, we can see this. This is fractional order system, and they have found that this type of chaotic attractors, and for certain values of parameters, we have Lyapunov exponent last. This is there is some positive, negative force right of in that also. Okay, so these are the chaotic attractors. Another kind of zeros or solution linear differential equation of second order. So they have this type of system, but this system has this solution. This is solution. This solution ratio of this applied this we get a new function and apply this function and generate a factors. So the region of a solution. So solution is like a vector. So next is a modified is a global fractional order system. So this is also fractional order system. So bifurcation diagram. So these bifurcation diagram are chaotic. And we have also partial differential equation, and they try to show that something this red problem also has a chaotic and fractal. So n equal to 2. They try to find the solution fractal, and this is also partially, but they also try to show that this fractal also we can generate through origami when we fold the paper. Okay? So we get also we fold the paper, we get a fractal, and also we can fractal generate through computer. Both things are same. And we go to our old designing of Indian culture, okay, our Arabian culture, we see that most of pictures like that. If we go old history and we see the designing, okay, on the old buildings, okay, now disappear. So where will we find, okay, we see the structure like a fractal, but that time they have generated by hand. Okay, they have it did by hand. But now same thing we can use little formula and similar design we can generate through fractal by using simple or some kind of difficult mathematical formula. We must need mathematics. Without mathematics we cannot generate fractal. But easy is this, now we can easily generate, once we have one filter, we can generate a lot of fractals. That's a small change. Okay. But in the old time we have one picture, finish. Second picture, you have to build again a year. Okay, and maybe we already listened many times in the old days, many king or many people, if they have design, they after that king said, no, you don't do this work for anyone and go away. Okay, so they just do only one time. But now we have option. So I don't go now in more detail because many people say I say fractal, a lot of picture are how why do we say fractal? Why do we say this chaotic? Okay. So we say because we can generate the dimension of a picture. Each picture has a dimension, and that dimension based on family dimension, box quantity dimension, household dimension, estimating a lot of dimension. We have a lot of name of dimension, but main thing is this: these dimensions are non-integer. These dimensions are non-integer. If these are integer, so just Euclidean geometry will work. Okay? Just Euclidean geometry will work. But if dimension is non-integer, then we say this picture is correct. So a lot of things behind that. So one of the definition just I have given, this is the self-limit. If we cut one third, so R is 1/3, and how many copies we get in the building? Sometimes 2, sometimes 4. Just put that, and we can find the easily dimension that by the intercept log 2 over log. Because when we cut 1/3, we get 2 pieces. So 2 log 2 over log 3. So this is non-integer dimension. When we cut the whole square, but we cut 1, but we put 2. So we get 4 lines, 1/3. So this is non-integer, same for other curves. So every time we have a non-integer time. So due to this, our picture in the beginning are fractal. Okay. So we have a proof for that. Those who are interested more, they can discuss with me. I can give you more detail. They can generate the pictures. Those are the fractals. So these are references. Okay. So now we finish here. Okay. This picture last 2 weeks before I went to Kazakhstan to attend a conference. And this is a picture in 2018. I visited Einstein House. That is a museum. So that time I have taken this. Thank you very much for listening.
Round of applause for the traffic team. Thank you, sir.
Next speaker is Professor Kanaya from Nepal, and he is the professor of mathematics. The probability of non-linear differential. Very interesting topic. The family is good. The topic of discussion is common fixed point. Good afternoon, everybody. Now we had a very interesting talk from our business center. My topic is common fixed point results with key compatibility. So I am from Bhopal University in Nepal. It's pleasure for me to be the part of this conference, and it is due to Hemant Kumar Desine, who just visited Bhopal University for one conference, and also Hemant Karikar. So I'm not going in detail about my topic, but it is very vague. So I will focus on some major results as well as some applications. So the plan of presentation is introduction to common fixed point. Why common fixed point? So it is one sort of extension to basic fixed point. Then the Banach crafting principle is the major source of research activity nowadays. And why we need compatible conditions? So our team at Bhopal University, and thank to my research scholars who have just introduced K-path compatibility and why it is necessary for the existence of common principles. And then I will discuss some of the common principle results without proof, and that will lead to some apprentices. So most of mathematics is focused on the solution. Why do we need mathematics? We get solution. And when you talk about solution, then it is very basic, whether it is exact or approximate, of various equations like differential equations. But my aspect is function equations. So involving numbers. The nature of the solution to a problem always helps to analyze the system for solvability, whether the solution exists or not. Stability is one of the important part of that deals with the system and the smoothness of the solution. So many equations which are of interest in applications can be put in the form of Tx is equal to x, and that is the function equation. So right now, we will start to discuss about the fractals and chaotic system. That is one of the beautiful applications of fixed point, and that deals with the single map, where the T is the self-matrix of the metric space. A point x which satisfies this function equation is called fixed point of the map T. And you can find many of the good things in the literature. So I'm not doing it. If you go to the first definition, then the point x naught in x is fixed point in A of x naught is equal to x naught. That's the very basic definition. But when you are trying for the two pairs of mapping on the same domain, then automatically you have common fixed point.
either common fixed point or coincidence points. So this notion is that when you move to the bidimensional or multiple functions of the same space, then it is not easy to get fixed point. For that aspect, you need some more conditions, and that's why we need compatible conditions. So if you classify fixed point theory, this is one of the important domain of nonlinear analysis. We have three divisions of nonlinear analysis. One of the important division is fixed point theory, and that is my research domain. I'm not an expert, but I have some of the good results there. So three domains are topological fixed point theory. Another is the metric fixed point theory, and nowadays due to graph theory, we have discrete fixed point theory. And my research domain is connected to metric fixed point theory. I love my research in metric. So metric fixed point theorem, this theorem is very important. Banach fixed point theorem. The contraction mapping T on a complete metric space X of T has a unique fixed point in X. And the same form, this contraction we have in mathematical form, this one, distance between Tx and Ty is less than equal to T of distance between X and Y. And this, the value of K between 0 and 1 has been crucial role. So now if you check it, then you can find a double star because this is very important for the current research what is going on in the fixed point theory. So the first is the completeness of the metric space and its subspace. And if you find 19 plus, recently my scholar has discussed about some major spaces. So now with 20 variants of the metric space. No, not some only variants, major variants. We have 20. Then extension of single pair to two pairs or sequence of pairs. So Banach contraction principle is connected to single mapping. So whatever you are getting applications of Banach contraction principle, that is fully single mapping, like Keynote and Packers. But if you are dealing with the two pairs, single pair, multiple pairs on the same domain, then it is not so easy to get fixed points. That is the major challenge. So generalization of the contraction condition, we have now additional compatible condition is very important. And we have now 23 plus. So that is necessary when you go to multiple functions to have common fixed point. So this is very important part where we have the research activity now. Necessary conditions in Banach contraction principle are contraction, completeness, and metric space. So the major source of further research activity is the metric space in the subspace. We have 20 like semi-metric space, probabilistic metric space. My work is basically related to fuzzy metric space, partial metric space is there, dislocated metric space. The single domain is sufficient to have many classical results there. Then the Banach contraction principle is connected to single map. You can be extended to pair of mappings, or two pair of mappings, or three pair of mappings, and even you can extend it to a sequence of mapping. That is another part. So in this case, we can find that in the historical aspects, we have the Kalman type mapping, mean killer type mapping, absolute delta condition, wide mode type mapping, Chatterjee type mapping, Jarrell-Ferescu type mapping. So these are some initial contraction conditions connected to Banach contraction principle, and interestingly, all these conditions are connected to single cell mappings. Additional conditions of the pair of mappings for the existence of fixed points. That is very important because if you want to extend the functions, then automatically you need some stronger conditions. That condition conditions. So semi-compatible, weakly compatible mappings. So if you are interested, you can go to this paper, fixed point theory application 2014, and that gives you the connection of all compatible conditions. So this is very good source for the young research scholars. So initially compatible mappings were discussed by Young in 1986, and then his team discussed about the compatible mapping type A, then compatible mapping type B, and compatible matrix of type P. So we have different types of compatible matrix, and all are necessary for the existence of common principle. So Parker, Cho, and Khan introduced this type of mapping. Now this is called the compatible mapping of type C. And now on the basis of all existing compatible matrix, we have introduced new type of compatible matrix. So that is the compatible mapping of type K. I am not going in detail due to time constraint. So now our compatible mapping of type K is independent with the compatible of type A, compatible type C, and compatible of type P. And to justify all this, you need examples. It is not necessary that I will claim and then do example. In the classical sense, you need example to create to justify your results. So this is the example that gives the relation that our result is independent of the earlier existing compatible conditions. Similarly, this example is also important to classify different types of compatible conditions. Which one is more stronger, which one is more weaker. And now this is if you go to single variant, so using compatible matrix of type K, our team, I cannot claim that my team, but we have the team of which one who are working on the which ones. If you see, me and Partner Service are familiar since 20 years. But first time we met physically. Because due to his work, he had very strong research group in biological modeling. But I feel proud, and it is fortunate for me to see him directly in this conference. But since 20 years, we are so connected, and his contribution is remarkable in my university. So if you go just for the metric space, the metric space has 20 more variants. If you go to the fuzzy metric space, so we have now 19 extended forms. Then again we have the intrinsic fuzzy metric space. So this is just connected to single metric space. So we can extend it to fuzzy metric space, its subvariants, metric space, its subvariants, and then intrinsic fuzzy metric, its subvariants. So now I will discuss some of our results, whether we can extend our compatible mapping to intrinsic fuzzy metric space for the sequence of matrix. And the challenging part to develop example, be careful. To prove theorem is not so difficult, but to create example to justify the result is very challenging. It is not so easy. So we have just received answer, yes, you can extend, and this result has been just published in the Progress in Computational and Applied Mathematics. It is the Uzbekistan Academy of Sciences journal in 2014. Other results we have connected with the probabilistic metric space, that is the Mendel space. And now we have the publication in 2022. Another result we have just communicated and got positive result is in the fuzzy B metric space. So these are some new results we have established in the consideration for the journal, and we hope that it will be accepted. And these are some of our references that is connected to our work. So you can see some of the papers, some of the recent results, and it all goes to my research scholars. I cannot take the single responsibility of this. And with this, recently you can find there is 20 major methods of metric space itself. And one method is sufficient to have to establish many more results. And with this, I thank you all. Thank you very much. If you have any query, you can ask me, please. I think I'm on time. Any query? So some of the specified metric space is the original one. Then you know that the metric space has four properties. So if you change these properties, automatically geometry is related. If you look at geometry, we have some generalizations, we have some extensions, we have some particular cases.
Which will cover all those properties. Topological space, which is not a such a space which will be also cover formalistic metric space, small metric space, or serial metric space, or G metric space, whatever. Then you can do the work as
no, this is not
what is trying to say is that yeah, we only cover the metric space. Yeah, I'm asking you possible and can be like the and then a thought or to say there is a same value can be defined all these spaces under one space. Right now, can be defined particular bigger space is all
right now it is not possible.
Authors or searchers are trying to find out different spaces. The one space and then they add something new. So maybe is a very only thing what we are trying to do some major changes, some small changes there, then we define that space. So what you try to find out is yes, if the mathematicians sit together and all the metric space are a new name, all these spaces come together, that's okay. But singularly the more than okay, thank you, sir. Obviously, you have something in mind, it will be surely underrated. So, thank you, sir, for your point and just reminded me of the old journey, etc. in the 90s. Thank you.
Thank you, sir. I request you to please felicitate some people of this discussion. A big round of applause.
Next is Mr. Recosta, Mr. Recosta. Your topic is some quantitative results for the first order non-linear Navier dynamic equations. You are ready?
Good afternoon to everyone present here. I'm Rachel Sarah, a research scholar from Bhopal University. And the topic of the paper is ultimate results of first-order non-linear Nabla dynamic equations on time scale. This paper was jointly written by Dr. Zen Lobo and Dr. Sanket Kale and Mr. Suraj Karnekar. So this is a brief overview of the presentation. So I'll start with the motivation. Basically, the dynamic equation on time scale is basically a generalization of different equations in distant spaces and differential equations in continuous spaces. So the Nabla derivative that comes in the Nabla basically the analog of a backward difference operator that we have seen in different equations. So since we are working on a space that could be a combination, that is a combination of discrete as well as continuous, it is disconnected. And in such a case, in time scale calculus, there's a term called as jump operator. So back in 2009, the researcher, she had studied a non-linear first order Nabla dynamic equation without this terms of jump operators. But later on in 2021, 2022, Bona, along with one of the co-authors of this paper, had studied a delta first order dynamic equation which included those jump operator terms. Okay, so delta derivative is basically the analog of a forward difference operator. Now, the key gap that we found out was first is that this Nabla dynamic equation with these jump operator terms were not statically in terms of existence, in terms of the method of lower and upper solution. And then when we were working on this existence results and when we were coming to the uniqueness part, we realized that there was no suitable Conval inequality in Nabla derivative with the jump operator term that could aid results. So we came about. So just some preliminaries on time scale. So what is the time scale? Time scale is basically the domain on which we are working out the dynamic equation. Okay, so a time scale is basically any closed subset of R. Next, these are the operators that we are talking about, which are operators. So, for instance, if I take a space that is depicted in a picture, so you have a continuous part as well as discrete parts. Okay, so what is the jump operator? So the jump operator basically maps every point to the closest left neighbors. Okay, so for instance, the closest left neighbor of C would be B, and likewise of B would be A. Okay, and the closest left neighbor of A by the definition would be A itself, and likewise for B as well. Next, you have a concept of the Graininess function, which is given by mu t, and Graininess function is basically the difference or the distance between t and its left closest neighbor, that is OT. Next, under Nabla calculus, we have the Nabla derivative and the Nabla integral. Now, this Nabla derivative is not defined on all the points of your time scale T. It's defined on a subset of your time scale T called as T kappa. And this T kappa is basically a whole time scale minus 1 point. That is the minimum of that T kappa. And provided that minimum is X capital. Next, some key functions that we will see in our problem is one is Hilbert and continuous. Then is the Nabla exponential function. So under the Nabla exponential function, you can see again we have this, and that corresponds to the cases on top of the Nabla derivative. So if you look at the first case, that the argument of log is defined only if the argument is non-zero, right? And that expression can be seen in the definition of progressive. So to define the Nabla exponential, you first need the function to be a mu recessive. So this is the data dynamic equation that we had studied. And these are the conditions that which we took. And the jump operator term that Z rho T basically is a composition of your unknown function along with the backward jump operator rho T. Next, the highlights of this paper. So first is we studied the existence of the solution of this initial planning problem with the method of upper and lower solution. Two, we try to come about define or prove a stupid type of one-bar type of inequality to aid our results. Then we try to look at the Ulam type stability and the uniform stability of this initial planning. And we had some others supporting our ideas. We just go through the results. So again, the initial value problem, and these are some domains. So the first existence theorem we proved was we found a solution existing of this domain B infinity. And this theorem, the idea was given from was applied from Schrodinger's fixed-point theorem and as well as theorem. And then for theorem 2, what we have done is we have proved that a solution exists for the subset of that of B infinity. So basically, it's and it's very sure that the solution is bounded by the solution of the solution that exists. Next, we come to the uniqueness result. So, this uniqueness result and a Lipschitz condition. And you see that Lipschitz condition again, it varies from the Lipschitz condition that we see for differential equation because it has that both term. So again, these two modified format and inequalities that came about. So one was with a constant dot, and two was with the equal dot. So this example is an example based on the second theorem, and we try to show that if you take the lower solution to be 0, then you have a positive solution in this case. Next, we looked at the convergence of the solution. So first, we formulated operator A, and then we brought out an iterative scheme where you apply the function repeated to itself, composition, and then proved a theorem that said that these closed solutions are basically the zero approximation of the solution Z. So zero approximation basically that the sequence of the sequence that we thought about with respect to the solution should converge uniformly to the unique solution Z, which we have found in the previous result. Next, we come to the stability of solutions. So first, what we did is we proved the continuous dependence of the solution to the initial condition. And using this equality, we proved stability and uniform stability. Now, the key inequality which we have taken uses that log-1 inequality which we proved. Lastly, I will come to the Ulam and stability. So, for the stability results here, we first remove these conditions. And under these conditions, we found that this solution is HRS stable. Okay, that with the HRS function as lambda into the exponential function, and the probabilities of this HRS theorem were given below. Were basically a generalized HRS higher num stability and generalized higher num stability. Okay, so basically in this theorem we used the abstract non-bar lemma which includes a Picard operator. So we have to construct the Picard operator and then apply the lemma. Lastly, again it's just an example. There will be a time stability Z, and it basically shows the result in here on charts. So to conclude, so we took a Napa dynamic equation which was order and non-linear, digital banking. So thank you. Any questions? And these are my references.
Thank you, sir. Presentation. Next is online approach. And your topic of talk is more about functionally the bank capacity component. Good afternoon, everyone. My name is Kothri-Kalan from MIT Manipal. So today, topic of that I am going to discuss is co-binary notebooking quasi-complete matrix spaces. So this is a continuation of one of my papers on co-binary notebooking quasi-complete matrix. So the basic motivation is that compactness and the completeness are among the most fundamental properties in matrix spaces that has been thoroughly studied for last few decades. So, if we look at the definition, so completeness means every quasi sequence has a convergent subsequence, and compactness means every sequence has a convergent subsequence. So, if we look at these two definitions, so one is every sequence, and another is every quasi sequences. So, between quasi and every sequence, so there might be some other sequences which are not quasi. So, can we characterize? So, we may use those sequences to characterize matrix spaces which are not complete or compact, but may show some property related to those matrix spaces. That is the motivation of study. So one such generalization is the concept of UC space. So basically, the definition of UC space was introduced in such a way that a matrix space is UC if every real value continuous function on the matrix space is uniformly continuous. But later it has been found that we can characterize UC space by convergence of a pseudo-quasi sequence. So another property of another such matrix space which lies between complete and compact matrix space is called co-finally complete matrix space. So by a co-finally complete matrix space, so it's a matrix space where every co-finally quasi sequence has a cluster point. So that we are again characterizing one such matrix space by a sequence, convergence of a particular type of sequence. Here we are considering co-finally quasi sequence. So in the definition of quasi sequence, if we replace the residual set by co-finally set, then we have the definition of co-finally quasi. So this space later has been characterized not by a sequence, by a different type of geometric functionals, also by functions. So in particular, by using Lipschitz type of functions, some Lipschitz type of functions, we can characterize UC space as well as co-finally complete matrix space, and also behavior of functions. Like if a function picks up certain type of sequences, then we can use those functions to characterize UC space and co-finally complete matrix space. So in this direction, another interesting property is called chainability property. So we say that a matrix space is epsilon chainable if any two point in the space can be joined by an epsilon chain. So what we mean by an epsilon chain? Let's say in this case we have
2 points x0 and xn. So we can join, we say that x0 and xn can be joined by an epsilon chain if there exists finitely many points between x0 and xn such that it satisfies the distance between x0, x1 is less than epsilon, x1, x2, so on. Okay. So then we have the concept of Burgoschi bounded. It's similar to the concept of totally bounded matrix space. What we are doing, we are saying that a space or a subset in the matrix space is Burgoschi bounded. If each point of the state can be joined so there exists finitely many points in the space, and each point of it can be joined by some epsilon chain of particular length to that point for each epsilon that we can get. So that's why the another name for Burgoschi boundedness is finitely chainable subset. Okay, so to characterize the subset, so Jericho and Medano have to introduce two more concepts, more sequences. One is Burgoschi sequence, another is co-finally Burgoschi sequences. And in the same paper, they had to introduce the concept of Burgoschi complete matrix space and Burgoschi co-finally Burgoschi complete matrix space. So if we just look at the Burgoschi definition, it says that for each epsilon, there exists a certain term of the sequence. After all terms can be joined by the epsilon chain of certain length. So in this case, so that length will depend on the choice of epsilon. So obviously, for co-finally Burgoschi, we have to replace the residual set by an infinite or infinite set or whatever co-finite set. Yes. So again, these spaces also can be characterized using some particular type of functions and also functions which is a particular type of Cauchy-like sequences. Okay. So in recent years, also there are more study in this direction. Instead of saying that each point can be joined by a particular length, we can say that each point can be joined by any length. And we have the concept of EC pre-compact matrix space. And eventually they had the concept of Burgoschi complete matrix space. And later in 2024, the concept of co-finally Burgoschi complete matrix space has been introduced. So in one of my papers, I have been characterized those matrix spaces using some geometric functionals. So I have to introduce some new geometric functionals to characterize those type of matrix spaces and also certain type of open covers. So, but there are some natural questions still unanswered that I'm going to answer in this paper. So, as we have seen that usage spaces or co-finally complete matrix space can be characterized via Lipschitz type of some particular type of Lipschitz type of matrix. Can we do the same thing for this co-finally Burgoschi complete matrix? So fortunately, yes, the answer is yes, but we have to add something extra to the space to get the characterization. It's not going to come naturally like that has been for other spaces. So here we have to make little more addition. So the next question is, can the function that is a co-finally Burgoschi determine this type of completeness? Here the answer is no. So we did not get the thing we got for other matrix spaces. So we'll see some example for that. Okay, so then we have asked do such a categorization extend to the completion of a matrix space? Okay, so we'll give some equivalent condition to categorize completion of matrix space. So these are the thing, some standard definitions that we must know. Like all we know that definition of local ellipsis function, which says that for each point we get some radius, and on that finite, on that ball, it is ellipsis. Okay. And Cauchy ellipsis means function is ellipsis on a range of Cauchy sequence, and uniform means that it's a local uniform ellipsis means it's a uniform that radius can be chosen. Okay. So this is the concept, or this is the type of ellipsis function we need to use to characterize this new complete this properties. Okay, so the concept is what we are saying, a function is strongly uniformly local ellipsis. If there exists lambda such that if we consider lambda component, so what we mean by lambda component means it's a if you look at that, h d infinity x lambda means the collection of all those points which can be joined to x via lambda chain. So if A is Lipschitz on each lambda, each such ball, each such component, actually not ball, then we call this strongly uniformly local Lipschitz. So obviously every Lipschitz function is strongly uniformly local Lipschitz, but the converse is not true, and also that strongly uniformly local Lipschitz functions are uniformly local Lipschitz. Also, we need this concept to characterize. So, as I said, that we cannot directly characterize. So, we have to consider strongly uniformly locally bounded matrix space. So, we say that a matrix space is uniformly locally bounded if there is the delta. So, and if for each x, the delta changeable component that is bounded subset of x. So just keep this. So this is the first result we got. So here in this result we are characterizing x is cofinally Borgo equal to complete matrix space. Just look at the last. So it is equivalent to say that x is strongly uniformly locally bounded space, and every real value is strongly so it's saying that x is uniformly Borgo equal to complete even only x is strongly uniformly locally bounded, and every real value is strongly uniformly locally function are uniformly dense in the class of all continuous real value continuous function. Okay, so here we have characterized completion of a matrix space. We say that the completion of a matrix space is cofinally Borgo equal complete is equivalent to all these conditions. I just consider the third condition. It says that x should be strongly uniformly locally bounded in itself, because all these properties are variation in nature. So that's why bounded in itself is that word is important, and every real value positive Lipschitz function on x is uniformly locally chain Lipschitz. So here is another more characterization. So here we used Lipschitz. We say that our space is uniformly Borgo complete if the non-vanishing, if we have a non-vanishing strongly uniformly locally bounded function, then the reciprocal of that function is also going to be uniformly locally chain Lipschitz. Okay, so these are few more characterizations. It says that we can characterize a family of strongly uniformly locally Lipschitz function. Pointwise, there if you multiply to such function, it will be the same if and only if x is strongly uniformly locally bounded space. So here is one more characterization. So I'll skip this. So in here we are basically characterizing cofinally Borgo complete matrix spaces, not via using Lipschitz type of mapping, but instead a mapping which sent. So if you look at the condition, fourth condition, it says that x is uniformly locally Borgo complete. So first one is Borgo quasi-complete, and the last one is Borgo complete. And every cofinally Borgo quasi sequence in X is a Borgo quasi. So by this, what we are doing, we are basically establishing relation between existing concept of completeness with this new concept of completeness. Okay, and some extra added on. Okay. So again, this is another such characterization. What to add with complete matrix space to make it cofinally Borgo quasi-complete matrix space. It's for the result for the completion of such type of matrix space. Like, suppose the completion of the matrix space is cofinally Borgo complete. So what to add to make it completion is co-finally verbally quasi complete. Okay. And here we use some function which are starting type of quasi type of sequence. Okay, so these are the references. Any question? So this function depends on the distance function with the matrix or without we can just take a any function just satisfy that condition. My question is there is a metric space, okay? So the matrix way to the distance. So this function depends on the distance function, or we can take just a function just satisfy these conditions. Based on the choice of metric, we have defined on the state. Change the metric of the state. Same concept might not be. It's some generalized to the step compression also. They don't depend on the compression principle. They will do the solution. So just they based by the any function. So the function will be depend on the directly compression principle. So there is a I think the function is not dependent on the distance.
Okay, next is proposal. And the topic is investigation of Russian RPF dot QR user special. Please be precise.
Good afternoon, everyone. I am Inaugural from Dignitary University. Today, I am going to present on the topic investigation of Gaussian radar basis keyword pseudo-spectral method. And this is the outline. First, I have to introduce what is a radar basis function and some definition. And next, I can tell you that again function expansion of Gaussian radar basis functions. Next, method of radar basis function approximation, and next, numerical results and conclusion and references. First, let me highlight some introduction of radar basis function. Radar basis function method was proposed by Roland Martin and Iowa lecturers in 1968. When he first developed the first effective method for interpolation of scattered data. And later, it turns out was used this multiple-take basis function method to solve the partial differential equation. Since concept discovery, research in radar basis function has rapidly grown. The main advantage of radar basis function method is its exceptionally high spectral accuracy. And these are the definition. Okay, I will skip this definition. And I would like to highlight one remark that for a radar basis function, there is a step parameter this academic is very crucial in the study of radial basis function. Okay, mainly in order to solve the partial differential equation, the accuracy for these convergence of the numerical method is highly depend on this choice of center. And there are also many researchers working on how to choose this optimum set parameter groups. Here this is my polynomial definition, recurrence relation, and here is a Mercer theorem. Okay, according to the Mercer theorem, it says that every positive definite kernel A can be represented in terms of positive eigenvalues, lambda n, and normalized eigenfunction of an associated compact integral operator. So, for an kernel, a positive definite kernel, there is an eigenvalues and there is an eigenfunction, and according to Mercer theorem, we can represent that. Okay, one advantage of taking the Gaussian radial basis function is since Gaussian radial basis function is so we can present this Gaussian radial basis into according to the Mercer theorem values. Here, these are the results obtained from the work of Gregory Forster. Okay. So I will skip this. And there's also one remark that one of the sources of ill-tendency in the general basis function are these eigenvalues. Since when we try to interpolate with several large node, then the value of n will be large. And here we can see easily here the value when the values of n becomes large, this becomes it tends to zero. The interpolation matrix or whatever when you make a differentiation matrix, it will tends to singularity. So to take the inverse of that singular matrix is it is ill conditioned. Okay, and this is the method of radial basis function approximation. Okay, radial basis function approximation, as I already mentioned, is a robust and straightforward approach for effectively implementing and solving high-dimensional partial differential equation even in complex domain. Here are some of the radial basis function. Okay, in the table 1, I will skip. Here, in the direct radial basis function, we search for an approximate solution within function space bound by a set of constrained radial basis functions. The approximation of set T may be written in this linear combination of n radial basis function as given in equation 7. Here, we have to find this weight Wk for the time step for a time step n, and that combination. Okay, this here. Here, we can write our equation in the matrix form in the given in 9, and for n collocation points for the derivation of the differentiation matrix, we can write like this in the matrix form. Okay, where D is the entries of the basis function. And after the calculations, we got this differential operator. Okay, and using this differential operator, we try to approximate or we try to solve the partial differential equations numerically. And here use the QR algorithm. This QR algorithm is motivated. I motivated this work from this Gregory Forster and an MC code. Here, the QR algorithm. Okay, this coordinate matrix is decomposed into orthogonal matrix and orthogonal matrix. Here it is. Yeah, this. And here is the calculation. Okay. Now let me come back to the numerical results. After developing that algorithm, I tried to solve various partial differential equations. First, I tried to solve a linear partial differential equation. And when I try to solve the linear partial differential equation, I will not face much hurdle. But when I try to solve non-linear differential equation, partial differential equation, it is hard to solve this non-linear partial differential equation. Since the method is I depend on two parameters, that is the set parameter that I already mentioned, the set parameter, and another is the global scale parameter. So we have to choose these two parameters wisely so that we can get an optimal solution. And when I choose the parameter with hidden method, I solve this equation, and here's a table comparison for different time step and accuracy. For example, to one-dimensional equation, I also solve it. And the third example, this Allen equation is a non-linear partial differential equation. When I try to solve this non-linear partial differential equation, Allen equation, this is a little bit hard for me to solve, and I didn't get the that optimum result or whatever result I want to acquire. Since these two parameters and how to choose this parameter is crucial, is a research area for many researchers also. So last few week, I came across what is that optimization theory. That is particle sum optimization. Using that particle sum optimization, I try to find two parameters. These two parameters, the parameter and the global scale parameter. With that optimization, particle sum optimization, I choose two parameters. With using that two parameter, I solve this Allen equation. And this Allen equation has no exact analytical solution. No. So how can I this with so that my method is good or my method is in order to compare, I compare with say from the no, that is from the Convert paper. From that paper, they use this spectral method to solve like this. And with that, from that paper, the graph is obtained like this, and my method also obtained the graph like this. Okay, from that conclusion, I can conclude that my method is also working. And these are the conclusions. And then we use numerical software, that is method software. These are the references. Thank you.
So we do very constant, there is no questionnaire. Last, Medicare, tell me. The topic of fog is numerical approximation of theory, non-linear, linear equation using local coordinate. Yes, you are friend.
Good afternoon, sir. Good afternoon, everyone. I myself, American Palmer, and I shall be presenting on this ICNACT 25, and I am a scholar from the Department of Mathematics at Bhopal University. This is my topic: numerical approximations of cubic nonlinear equation using local gas differential quantities. And these are some of the content of my presentation. Here we consider a generalized nonlinear coordinate equations, which is here given in equation 1, which has some special form like cubic nonlinear coordinate equations given in equation 2, which has found many applications like nonlinear optics, plasma physics, fluid dynamics, etc. This is the method that I will be using. This is a numerical approximation method to find the derivative of a function using weighted linear sums of all the collocation points within the domain. And according to this differential qualities method, the output derivative of this function is given in equation 3 at a point xi, where wij represented as the weighting coefficient. Here, this is a local Fourier-based differential qualities method. This is a method that is derived from the differential qualities method. And according to this one, for n partitions of AB, and followed by this is adopted by the SU, and for n point xi, we consider as tangent size of k plus 1 frequent. And for a left boundary, I take k2 is equal to k, k1 is equal to 0. And for the right boundary, I consider k1 is equal to k. And according to this, the angular derivative of this function is given in equation 4. Here, according to the method, the first order derivative, that is wi plus j, the first order derivative of weighting coefficient is given in equation 5, where g1xi and g1xi plus the other. Here, the local Fourier-based differential qualities weighting coefficient for the following second order derivative that I shall be using up to second order derivative is given here in equation 6. And for the diagonal coefficients, wi for n of the derivatives, I take consider here in equation 7. Once we got the weighting coefficients, we computed the following differential matrix that is given here in W1, W2 to approximate the first and second order derivative of the function. So, in order to implement the equation 2 of cubic nonlinear coordinate equations, I consider this initial and boundary condition, equation 8 and 9. And this cubic nonlinear coordinate equation I convert into couple initial and boundary value problems here in equation 10. And after that, this cubic nonlinear coordinate equations using differentiation matrix that I have. So before we apply in this cubic nonlinear coordinate equations that to convert the partial differential equation to ordinary differential equations using this differentiation matrix with this initial and boundary conditions. So the result of this equation 11 will be solved by using Runge-Kudar-Four method for the time derivatives. And for the accuracy method, I use L infinity, and for the two lowest invariants, C1 and C2, here given here. And firstly, I take the single soliton, which is represented here in equation 14, which is the exact solution of the single soliton, where alpha, sigma, Q1, Q are the conditions within the domain minus 20 to 20. And this is the result of the L infinity error comparing with the earlier with the earlier papers. As we have seen that the L infinity is more, the error of this L infinity and C1, C2, they are more accurate. And similarly for alpha equal to 2, I also compare the results for L infinity. And this is the motion of a single soliton wave at different time level. And then this another one is double soliton. We consider initial conditions of this double soliton given here in equation 15, where W1 and W2 are the initial condition. So from this fluid solid interaction, we have seen that even after interaction, they retain their shape and size when the amplitude loss. And this is double soliton, which is interact at a point in time t is equal to 2.5. And if even after interaction, they retain their self and size. Here we see that the two lowest impedance C1 and C2. Compared with the ironworks, this is also one of the consistent value for both C1 and C2, as given in the here. Next, last one is the mobile soliton. We consider the initial condition of this mobile soliton given in equation 16 with parameter q is equal to 2 within the interval of 45 minus 45 to 45. And this is a mobile soliton at p is equal to 1. That means the wave soliton, the solution of this wave diminishes part as the time goes. But when p is equal to 1.78, that is beyond the threshold point. The solution remains between self, size, and speed. This is one of the solutions of this soliton. And we have compared this C1 and C2 for n equal to 691 and n equal to 581. This is the invariant of mobile. And this is a mobile soliton at p is equal to 1. So in this paper, I have found that different solution of cubic nonlinear scalar equations using the method. And we have found that this method is far better compared with the exact solution and with the other results. The interaction of two solutions has also been investigated, and it observed that the solution retain their identities even after the interaction. And also the mobile soliton also observed, as we have seen in the figure, which clearly preserve the characteristic of this soliton as well. And we can see that this local differential qualities method, this can be also one of the best methods in order to find the numerical solutions of nonlinear scalar equations or any other nonlinear scalar equations. And these are some of the reference that I put. This is I want to conclude.
Thank you.
Thank you, sir. Now I invite our session 10 to give token of appreciation to all our participants, and I request all the participants to please come forward to receive their certificates. I request all the participants of this session to please come forward and receive certificates. I request welfare sir to please come forward. May I have a huge round of applause for ma'am? Thank you, ma'am. Next, I call upon Professor Anna Ghosh to please come forward. A huge round of applause for sir. Next, I call upon Inaugural Roosevelt to please come forward and receive the certificate. Thank you, sir. Last, I request Mr. Meredith to please come forward and receive the certificate. Thank you, sir. Now I request the chief guest to please give our session a token of appreciation for his conduction of our session so nicely. A huge round of applause for our session today. Thank you, sir. Thank you all for your kind cooperation. It was a learning experience to listen all of your exciting discussions. Now we will take a short break for lunch, which is being served at ED 425. After the lunch, we will begin our panel session. So I request everyone to please make sure to be back in your seats so that then we can begin with the proceedings. Thank you.
and esteemed session chair. It is my pleasure to introduce our session chair for this session, Dr. Mohammed Sajid, who is presently a professor of mathematics in the Department of Mechanical Engineering at the College of Engineering, Kasim University, Saudi Arabia. He received his PhD degree in mathematics at the Indian Institute of Technology, Kanpur, India. He also completed his postdoctorate under the National Board of Higher Mathematics Fellowship in India. His current research interests are real and complex dynamics, bifurcations, chaos, fractals, iterative process, stability, and fixed points, as well as with applied mathematics. Please join me in Dr. Mohammed Sajid.
Thank you very much for giving chance to conduct this session. So now we start this session. So in this session we have I think 7 talks, 7 presentations. So we call this one by one. So I hope you have already emailed your presentation. So I call one by one and you come and present. So first is now Dr. Asrifa Sultan. So her presentation on projected solution for generalized net gain energy.
First, thanks the organizing committee of the International Conference on the Analysis for giving me the opportunity to present this talk. The title of my talk is the predictive selection for generalized landscape, and we'll discuss about this. These are the outlines of my talks. First, I'll give you the brief introduction of the NAS problem. Then we go to the generalized NAS problem, and also be motivating by providing an electricity model which actually motivates us to introduce the notion of projected NAS behavior. So what is a NAS game? It's introduced by John Nash. Well, it is a non-cooperative game. There are 10 players. And each of the players' aim is to control a strategy variable x which belongs to a set n, and we denote that the total strategy by all the players are denoted by this vector x, where x is nothing but x minus n, where x minus n is the vector chosen by the diagonal players. So what is a NAS game? So for given any strategy chosen by the random players, that means to for any player new is to choose its new such that it minimizes this optimization. And what is this figuring? It is the decision of the player new. So he has to choose some x new over the set new such that this habits is minimum. So a analysis equilibrium problem is to find this vector such that the first vector solves this p new x bar minus mu, second one satisfies the x2 vector satisfies p new x bar minus 2. So minus 2 means except the vector 2, it will be remaining 2. So this I have given you a formal definition of the equilibrium problem. I will illustrate it with a simple example by prisoner's dilemma. So then the rest will be clear to you. So what is a prisoner's dilemma or a simple equilibrium problem? We assume that two members of a gang, they are named as A and B, they are arrested and they are in prisons. And they keep both of them in such a way that they cannot communicate to each other. So they are imprisoned in a solitary confinement so that both the members cannot communicate to each other. And also, what is the problem is the prosecutors has lack of evidence to convict them with a principal charge. But the prosecutors has a sufficient evidence to give them a lesser charge. So what the prosecutors do? He give them an offer. What is the offer? The offer is either you may confess or you can deny by getting silent. So, but the offer is if the A confess and B deny, then is the punishment of A will reduce and the punishment of B will increase. And anyhow, because both they have done some, the prosecutors have the minimum efficient that they can give you at least 2 years of imprisonment. So let's see the offer. So this is the offer we gave you that both of them in any case they will get 2 years of imprisonment, but if A confess B doesn't, then A's imprisonment will be reduced to 1 year and B will be increased by 10 years and vice versa. For if A denies, B confess. But if both of them confess, then both of them will get 3 years. Thus we can see the payoff matrix in this way. So for B confess and A confess, we get 3. B deny and A confess, it is 10. Again, B confess and A deny, it is 1 and this is 3. And the other side is also true for yes, A. So you can see that this is the Nernst equilibrium problem because if for the player A, what is the strategy chosen by the player B? If the strategy chosen by the player B is confessed, then what is the value for A? It is 3 and 10. If this is fixed, if this is confessed is fixed, then he can choose either confess or deny. So in this case, the value will be 3 or 10, so minimum is 3. Similarly, if the strategy chosen by the player B is denied, then it is for there is either 1 or 2, so minimum is nothing but confess. So confess is the actual equilibrium or the equilibrium of this game. So you can see that they both should have denied, then the optimal solution is 2, but it is not the next game because it is a non-cooperative game. You you can think about that, okay, I can choose the deny, but what other player will choose, you have no choice on that. So he can choose either country, so you have to take all choices of the rival players. So this is a simple NAS game with two players, and I have given you that this is actually the solution is 3-3, both of them will conflict. So I hope you have a little bit idea about the NAS game. So we can go to the more complex problem. So a generalized NAS equilibrium problem is nothing but a NAS equilibrium problem, but the difference is here the constraint set K is actually depending on the strategy chosen by the rival players. So it is not a fixed set, it is actually a kind of a function. K is a function from some C to C. So it is like a multi-value graph. So this is a generalized NAS equilibrium problem. So here you can see the constraint set is actually moving. It is actually constraint map, not a set. And then the vector is called NAS equilibrium. So it is nothing but X is the solution of this, and X has to be fixed point of the set A. Then it is called generalized NAS equilibrium problem. So this is for giving a solution to a generalized NAS equilibrium problem. As I told you, X has to be, or X bar has to be fixed point of the set K. So to have a fixed point of a set, it is necessary to have that it is that map. It cannot go to K from C to R. It will go to K from C to C. So it may possible, we will give a practical example that this constraint set need not be always set. It may be wrong set. In that case, the solution of equilibrium will not exist. And by that, we motivate to introduce the notion of projected NAS equilibrium. So it is not actual solution, but we are finding a best approximation or best NAS equilibrium from that. So I am giving an example of electricity market model, which you will get motivated, and you will understand what is the why you need to introduce the notion of projected NAS equilibrium. So we have considered a electricity market model, which is actually a generalized NAS equilibrium problem. So what it is, we have suppose we have assumed there are 4 producers of electricity. So each of them actually producing electricity. The quantity and what is the unique price for buying that quantity. So this first one is nothing but how much quantity they are selling and what will be the price for unique quantity for that electricity. So they all the agents send their data to the ISO. ISO is the independent system operator. It is a government organization who actually buy electricity from the different producers. So sometimes you have nuclear, sometimes you have what is called water. So all kind of different type of electricity, maybe same type, but there are many different agents or different producers. So the government organization, what they do, they buy the electricity from the different producers, and they decide that how much quantity I want to buy from this one and this one and this one. So this Q1, Q2, Q3, Q4 is the quantity the ISO decide to buy from this agent. So what is the motive for the ISO? The motive for the ISO that the demand should be satisfied of the country, and also the cost of production has to be minimized. And what is the motive for this each producer? To maximize their benefit. So the problem is actually mathematically look like this. It's a bi-level problem. So the problem for each producer is nothing but this actual cost and this is the selling price. So this minus this is the maximizing such that Q solves the ISO. The quantity solves the ISO problem. And what is the ISO problem? To minimize the cost of production and suppose that demand is satisfied. That something of all Q1 has to be greater than equal to the demand. So this is actually the mathematical problem, and this is nothing but a generalized game. So in this electricity market model, what happened that this beat function what each producers are giving, this each of the producers are sending to this isotope, they are actually kind of a step function or piecewise function. So when we will actually write the mathematical model for this generalized accessibility problem, because step functions are not differentiable, it will be piecewise. So the computationally it will be very difficult. So what the aim is, so each this is the kind of the step function, or we can have this kind of piecewise function. So what is the idea? We can approximate each of these step function by quadratic function. So if this is the step function, we are actually approximating it by quadratic function, even for the piecewise function. In this case, by approximating this each of the step function, this k is or involving constant map is not become self. It is a non-self. So the problem is actually coming to a generalized possibility problem with constant constant map. And here we are actually noting to, so because it is not that it doesn't have an equilibrium, so we are finding a projected equilibrium which will be closer to the equilibrium of that problem. It is not exactly, but it is the like a best approximation, or it has minimum distance with respect to the norm involved. So this is the model. So after approximating its function, the model consists of finding a vector p bar such that there exists a quadratic wave function y bar, which is actually the best approximation in sense of L2 norm corresponding to all vector quadratic function y bar, and it is this each for each time this y will satisfy this game on that game. So a beat function p bar is said to be best approximation, or is said to be projected as equilibrium if it is the best approximation, or this y bar is the best approximation, and also y bar satisfying the corresponding aspect. So what we are doing, we have a kind of a domain, and it was C the one set of beat function. So we are actually approximating each of beat function to a set that is actually K3 and which is non-self. Then we are taking approximation of each of them, and from this we are solving the landscape. So our problem is this now this y is a quadratic beat function, it is differentiable, so we can solve this maximum problem and we can get the y bar. And for that y bar, if we get the minimum of p bar, we will go to the predicted escape. So from one system we are changing to another system, and how it is we are going, we are choosing which is the closer one. So this is by electricity market model. I have given the motivation example, but what is the actual projected accessibility problem definition? So this is for a general definition of a projected landscape. So let's see we are already subset of variable. Theta is the objective function, k is the constant map, which is we can see it is non-self. And the point is said to be projected solution if there exists a y bar such that x bar is the projection of y bar, and also meantime y bar solve this. That's it. This is the existence result that we have proved. So this is not come just by default. If we have proved through various inequality problem, if you know the name. So variational, first we have put the existence result for a variational inequality problem with constant constant map. After that, by taking a particular variational inequality problem, we get this landscape existence. By using this result, we have also proved the projected landscape medium for the electricity model that we have just presented. So under this kind of assumption of projected model, we have proved that based on this result, we are able to give a projected landscape medium for the electricity market model. this is the work that we have published, but now actually we are doing a specific solution for not generalized equilibrium problem, generalized games that we have recently done. So what is the difference between the generalized equilibrium problem and generalized game? So in this case, the electricity market model, you can see, will show the problem. Yeah. So here it was actually there are one objective function, but in that case there are two objective functions. So not only to this maximize the benefit, but also to minimize their initial production. So there was two kinds, one is maximum, another was minimum. So that is actually motivation for generalized gain. It is applicable to the multi-objective case. So here it is one objective, but then if you have more than one objective, it can be. So we have one part of the what has published and another is already being communicated. So I'll be very happy if you have any question and query. Thank you.
My name is Dignitary. I'm a research scholar doing my PhD in applicative approach of response results in nonlinear analysis. My research center is Development Engineering College, and my practice is the Computational. So today I'm presenting my paper based on interpolative matrix space and its application in nonlinear analysis. So these are the contents of my presentation today: introduction, main results, applications, and so that is the topic of my paper. Some new results in interpolative matrix spaces with applications. In introductions, hello. Yeah. The Banach contraction principle is the father of fixed point theory matrix spaces, and it has wide applications in solving linear and non-linear differential equations. And after last 2-3 decades, many generalizations have been done in this field. First, in generalizing the definition of matrix spaces, and then proving the fixed point theory on those matrix spaces, like B matrix spaces, B matrix spaces, vector value matrix spaces, quasi matrix spaces, and sorry. Yeah, so many generalizations has been done in the definition of matrix spaces, and then the mathematicians have proved the fixed point theorems on these matrix spaces. Then second generalization was in terms of generalizing the contraction principle on the matrix spaces, the definition of the contractions, and many great mathematicians have introduced Kalan, like Kalan contraction, Chatterjee contraction, Mild-Cadell, Ridge contractions, Siré-Cruz, Hardy-Rogers contractions, and the third generalization in this field was the generalizing the contraction conditions on the matrix spaces by introducing some functions like F mapping, theta mapping, Lotti functions, admissible functions, and all. Today in my paper, I use use these generalizations by generalizing my matrix spaces. I proved my result in very general. It is very recent generalization interpolating matrix space, and I use this F mapping to generalize my contraction, and I use this F mapping on sig type of contraction. So I will start with my work with defining some basic definitions. Like in first definition, this is a definition of interpolated matrix space. The first two conditions are common as it is in the normal matrix space. In the third condition, this kind of inequality has this interpolated form. Like the distance between x and y will be less than or equal to dxn, dzy, and c of dxn alpha dzy minus alpha for all x, y, z belongs to x, where c is a constant greater than or equal to 1, and alpha is a constant will belong to this interval 0 to 1. This type of the space will satisfy this condition, and with this distance function we will call interpolated matrix space. Obviously, if I put C is equal to 0 here, then this is nothing but a matrix space. So every matrix space is an alpha interpolated matrix space with C is equal to 0. These I gave 2 examples of my interpolated matrix space. Obviously, if one can see that the way I define the matrix spaces do not satisfy the normal triangular inequality, but they will satisfy this third interpolated triangle inequality for alpha is equal to 1 by 2, C is equal to 2 here in the first example, and in the second example for alpha is equal to 1 by t is equal to 1 by t, and C is equal to summation R1 from t to 1 is here. Then in the interpolated matrix space, as every matrix space is a topological space, our interpolated matrix space is also a topological space where the bases will be formed with this kind of walls.
where beta x is an open bond defined in this way. So with this open bond, the collection of all these bonds will form a basis of our topological space. Then the definition of convergent and Cauchy sequences will be like this in terms of the interpolative metric. There is an F function which will satisfy all these three conditions, that it is strictly increasing, its infimum will be minus infinity, and there is a third condition. These are the example of these F functions, and this is basic definition of an F contraction. I will denote all the classes of continuous and strictly increasing F functions with capital. Then one definition of psi. This psi is a function. It's a dynamically real value functions. Now here comes the basic theorem of my paper. Let X be a complete alpha C interpolative metric space and T be X to X be a generalized, almost silly type of F convention. That is, there exists one F in the class of capital N and the constant L greater than or equal to 0 and a function psi in this class. For these, with these properties, D, the distance function, the interpolative metric D, this T self-mapping will satisfy this condition. Then this T will be called slick type of F contraction on alpha C interpolative metric space. In this contraction condition, capital MXY will be alpha maximum of these three values, and small MXY will be the minimum of all these distances, and alpha, this constant, will lie between 0 and 2 upon 2 by c. So if T satisfies these conditions, then it will have a unique fixed point in the interpolative metric space X. So I proved this theorem by was proving the uniqueness of the point, and then I defined one iterative sequence. I proved that that will be a Cauchy sequence. Then with property of completeness, I proved that the sequence will converge to a point, and that point will be a unique fixed point of the mapping T. So these are some corollaries. If in my basic results, if I put N is equal to 0, then I will have this contraction, and for this contraction T on this complete interpolative metric space alpha C, this T will have a fixed point. There is a second corollary. If here in this condition, if I take the function f of x as log x and the tau is equal to 0, then I will have this result, and this will give another a new contraction T on complete interpolative metric space alpha C, and for this result also our T will have a unique fixed point in the interpolative metric space. There is the third condition where I put L is equal to 0 in my basic theorem, and if I take dxy, this also in the previous corollary, and if here mxy is maximum value of these three terms, then T will be a contraction which will have a unique fixed point on the alpha C interpolative metric space. And this is the last corollary where if L is an almost F type of contraction, this will be a particular case of the basic theorem, and in this case also T will have a unique fixed point in the alpha C interpolative metric space. Can I give an example? Here X is the closed interval 0, 1. It is an alpha positive metric space for alpha is equal to 1 by 3 and C is equal to 3. If Tx is like this, defined like this, then for these values alpha, L, psi, and F, this T will be almost F as a contraction on the interpolative metric space, and will have a unique fixed point on the space. Then I gave, as I am doing, there is this in the application of fixed point theory in nonlinear analysis. I give the application of my theorem into non-linear integral equation. The first is discrete mass system. This is the differential equation. This will be the integral form of the equation, which is non-linear integral equation. Here GST is a green function defined by like this, and if I define my metric T like this, then this will have interpolative matrix on X with alpha is equal to 1 by 3 is equal to 3. Then I will prove with this theorem that this T, if I define like this operator will satisfy all the conditions of matrix A theorem and will have a unique fixed point in this space, which will be the unique solution of this problem. For to prove this, that this T will satisfy all the conditions of basic theorem, I put the three conditions. This T should satisfy, and this function also. So these are my three conditions. Here I prove how the T will satisfy all the conditions of the basic theorem, and it will have a unique fixed point. Then the second theorem, the second equation is application solution of ordinary differential equation. This is the first order periodic equation. Here again, I define dxy like this, which will be again an interpolative metric on the metric space X, which is this collection of all continuous and bounded function between I to R. Alpha will be 1 by Q, so we will be summation of n that is from 1 to Q and CR. Here again, I give this theorem to prove that the integer operator F U T will have a unique fixed point in the given space. And I prove my theorem to show that here also the operator will possess a unique fixed point in the given space. These are the references. Thank you very much. Sorry. It is yeah. Suppose greater than 0 explosives and then upon wall alpha interpolative matrices X is open wall form the basis for the topology induced correctly. Here the structure induced by the parameter alpha is reflecting the interpolative nature of the matrix. So only definition in the metric is only the third parameter represented in the form. This is just it is I did not find it. I only take it from Kothri-Kalan, who is the father of interpolative matrix. So I took the definition directly from there. Numerical applications, I will let me find it out. Right now, I did not work on that. I work in 2-3 of my papers on the same space. You are absolutely right. We can prove that it is error automatically. So numerical in this paper I already Thank you everyone.
all of you. My name is Kumar. I am a research scholar at the Department of Mathematics, Aligarh Muslim University, under the supervision of Dr. Kothri-Kalan. Today I will present my research work on the topic ideal convergence in microscopic form space defined by other metrics. These are the presentations outlined. These are the historical background. First, we will generalize the concept of visual convergence and negative statistical convergence. After 50 years of statistical convergence, the ideal convergence is stronger concept than statistical convergence, defined by Professor Kothri. Now, we the history of the set, and philosophic set. The real world problem may not seem practically real when it comes to assigning mathematical behavior to the event. The application part of the mathematical analysis usually incorporates classical visual logic, works on the concept of yes or one and no or no. One such example can be considered as a set of all buildings that lie in Mumbai, to which mathematical value 1 can be assigned. And buildings that lie outside be assigned 0. Only the stated expression can be defined in terms of the characteristic function, which is defined as fx equal to 1 and 0. 1 if x comes to a and 0 otherwise. If we relate the condition from the buildings lying exactly in Mumbai to the buildings that lie in the vicinity of Mumbai, the problem arises to know the extent to which a building lies near the city and far the city. The concept of assigning numbers as 0 or 1 to the buildings become a little tedious because some buildings might lie in the city, some may lie on the boundary, and some will be outside of the city. With the boundary and outside the boundary. This means we need a generalized form of this characteristic function to gain not limited to just 0 or 1. To overcome problem of this sort, Harry in 1965 came up with the concept of a function. According to his theory, in this case, the characteristic function should take values between 0 and 1 along with 0, 1, which we term as a membership function denoted by mu as a generalization of the characteristic function. Formally, he defined the petition appear A equal to x comma mu, where x is the space of objects and mu is the membership function. Next, one can extend the idea of vicinity used in case of fuzzy set in terms of its membership fraction. One can consider the building that lies within area of radius 200 kilometers in the central Mumbai to be near the city, and those that lie outside the area of radius 250 kilometers of the Mumbai to be far from the city. Here a relative confusion arises as it has to be done regarding the building that lies within the 250 kilometers area. So there exists a confusion about the building's nearness or farness. This developed the base of construction of implicit concept theory, which was introduced by Adam. Even the concept of implicit fuzzy theory is generalized version of fuzzy theory and thus overcome the realized situation by incorporating a non-membership function. It is still limited within the boundary of efficient information and space process and terminated in such information. In other words, the membership and non-membership function in implicit fuzzy set are dependent on each other. That is, if one of them increases, the other one decreases, which may not be case in practical problem. That is, we say today is very, one says 50% chance and other says 40% chance. And other and third one says 30% chance is it is confusion or hesitation. So this is the to overcome these type of problems as presented in 2005 financial philosophy set. Now this is the history of Allen matrix. That here to be a right matrix here are complex entries, here entity spatial number, here you divide by this condition, here number. And this represents the transformation of the sequence U by matrix provided that right hand side converging over this number. Further, Furthermore, if Pn equal to 0 for all k greater than n and Pn equal to 0 for every reason for n, then Pnk is referred to as a random matrix. In this case, P possesses a unique inverse P inverse, which is also a random matrix having that determinant of P not equal to 0. That is where the P denotes a given sequence space. This space forms a decay space. Now by this condition, if and only if there is a decay space and P is a random matrix. Suppose that the Allen matrix of order R denoted by here, find S and infinite matrix here. Here is it defined by NCK 1 minus R power n minus 3 R power k is the line between 0 and n. And here at 0 is k is greater than n. The Allen matrix has been divided into the study of sequence space and over the classical entry space. It is considered a boundary operator. Recently, we have and F and Muslim investigated sequence spaces PRS consisting of all sequences through that transform belongs to LPN and infinity. Now, we come to the basic definition. This is the definition of Newton dialectical and subset E, subset of Newton number, and by this condition first. Next definition is statistical conversion. A sequence x equal to x is statistical conversion where for all SRI the density of the set will be given. Where we have k less than equal to such that not k minus n greater than equal to epsilon. Now next definition is ideal. Let x be a monopoly if value of subset I subset of all set of set is R and ideal from x if each a belongs to I implies a belongs to I. So each a belongs to I and each subset of A implies B subset of B belongs to I. I started from figure is x and what belongs to I. Next definition is interassociated with ideal I. Let x be known as set if value of subset expanded function of x. If for each A belongs to F implies A intersection B belongs to F. For each A belongs to F, B contains A implies B belongs to F. If I is non-trivial ideal in X, then X is non-empty, then the class F forms a filter of X. This is the definition of Q1 and Q1. This binary operation is that defined on 2 0, 1 is said to be a continuous Q1 with these four conditions are satisfied. Then circuit is binary operation defined on 2 0, 1 is said to be continuous Q1 if these four conditions are satisfied. This is the definition of philosophic norm space. Let star be a continuous Q1 and circuit be a continuous Q1 and X be a linear space order and Z be a philosophic set. Such that set X was open into 0, 4 into 0, 1, the fold of X then star circuit is party philosophic norm space. Is the substitution of here the three terms gamma 1, gamma 2, gamma 3 are the gamma 1 is the membership function, gamma 2 is the registration function, and gamma 3 is the non-membership function. Now, this requires the definition of either I conversion. Sequence U is said to be either I conversion to gamma is for every epsilon greater than U. The set next definition is sequence U equal to Y of W is said to be either lossy for every epsilon greater than 0. There exists a Newton number k depending on epsilon such that the set belongs to Y. In this section, we introduce a new capital sequence spaces formed by applying the Allen transformation to the sequence U with respect to the additional Allen and this topic. This is the convergent sequence that we are not convergent sequence. What is preferred in this slide is that we show the sequence is for non-convergent sequences and by ideal in this topic norm. By using the Allen convergent and this topic norm space we find sequence that to be because of the Allen convergent with respect to the because of the norm gamma 1, gamma 2, gamma 3 denoted by dy and gamma is for every epsilon line between U and 1 and in character A greater than U, the set becomes belongs to Y. Q1 is denoted by parallel policy with respect to Microsoft norm, gamma 1, gamma 2, gamma 3. If for every epsilon 9 between 0 and 1 and a greater than 0, there exists a natural number k such that the set to belongs to I. We have four results from the sequence spaces. These are the basic results from the sequence space. The spaces Ci and C naught I are linear space. And sequence U is said to be either I convergent with respect to Microsoft norm if and only if for every epsilon greater than 0 and a greater than 0, there exists a number n such that this set belongs to the filter associated with I. Next level is sequence in Ui is Microsoft parallel convergent, then this limit is unique. Next is sequence U is Ui from W considered Microsoft parallel convergent with respect to the Microsoft norm. If and only if it is Microsoft parallel policy with respect to the same. Now I am working on the next property of sequence space like a topological property in this case and in this paper we presented the idea of identity convergence by using the Arlen matrix transformation in Microsoft monospace, and this paper covers important information to user research in the area of convergence of sequences. One can prepare sample papers from field of approximation theory and fixed point theory by defining different extended sequences. These are my differences. I have used. Very strong, how to justify it. I'm working in the property and nothing because I have not like that's strong and how to justify it. I say that I know. Okay, but it must be the example. I do it for I say example means I say we have a map. That is not a true thing. We have a map. This is obvious. I don't know this or this. But how to make this building? What is the building? I don't know. If they have and this I said this is a computer. How said this is a computer? Just you say in our network this is there. When I review, I said it and what you do, you must have the certificate. From a university. Today I'm here to present my research finding at the second international conference on non-Indian analysis and computational techniques. The title of the presentation is Analytic Framework of Futuristic Fuzzy Quasi-Normal Spaces via Ascending Families of Alpha Quasi-Norms. These are outlines of my presentation. I'd like to start with the historical background and motivation of polynomial spaces were initially introduced by Carl in 1984 and later defined as separate using the label similar type method. In 2003, Bag and Samantha proposed a modified polynomial to prove the decomposition theorem and on the fuzzy function analysis. On the other hand, 1999 Haskell introduced linguistic fuzzy set incorporating both membership and non-membership functions. This led to the development of linguistic fuzzy norm spaces by SASL in March 2006. Inaugural introduced fuzzy quasi-normal spaces in 2010 by relaxing symmetry and later proved results like uniform ordinance theorem in 2022, who and he expanded the open mapping theorem and closed graph theorem to this framework. Recently, Khan and his co-authors introduced impressionistic fuzzy quasi-normal spaces by combining quasi-normal symmetry with impressionistic fuzzy norms. While fuzzy quasi-normal spaces have advanced significantly, the corresponding impressionistic fuzzy framework that captures both symmetry and both asymmetry and dual membership is still less comprehensive development. This is a motivation. In 2020, Gao established the decomposition theorem for fuzzy quasi-norms using families of star quasi-semi-norms. Later in 2022, Wang and Wu provided operative criteria for normal continuity in the placement. Motivated by these advances, our work seeks to extend these ideas in impressionistic fuzzy quasi-norm setting. This is the contribution. First, we define a family of alpha quasi-norms from an impressionistic fuzzy quasi-norm and describe its behavior. Then we provide a decomposition theorem that links impressionistic fuzzy quasi-norm with an ascending family of quasi-norms. Finally, we extend this framework to define operator quasi-norms for strongly impressionistic fuzzy quasi-bonded linear operators. These are some basic definitions. Now we recall the definitions of continuous norms and T-low norms, which are the generalization, which generalize the concept of intersection and union in fuzzy set field.
also introduced the concept of interpolated reduced type convection. In 2012, Summit Detail introduced the concept of alpha admissible mappings and proved several fixed point theory for this class of mappings. In this context of complete matrix space, inspired by the concept of alpha admissible, Dr. Detail introduced a new class of alpha KSP admissible mappings and also defined alpha KSP sci-fi context mappings and proved various fixed point reasons for this mapping in complete B matrix space. By adding this idea of alpha admissible to interpolative kernel and select research type contraction, they introduce alpha interpolative kernel type contraction and select research type contraction. In 1989, Berkeley introduced the concept of a B matrix space as a generalization of additional matrix space. He established the contraction mapping principle in B matrix space, extending the classical Banach contraction principle in matrix space. Stephen Zell made B matrix space popular among researchers in fixed point theory. Motivated by the above mentioned work as well as contribution of General Intel, who introduced the notion of alpha KSP, admissible and alpha KSP sci-fi contraction. In this paper, we introduce alpha QSP interpolative kernel type contraction and research type contraction. By using these new contractions, we examine the existence of this point in B matrix space. This is the definition of B matrix space. Alpha admissible mapping is introduced by Summit in 2012. X is non-empty set and alpha from x cross x to 0 to infinity be a function. A self-mapping P x cross x2 x is called alpha admissible mapping if satisfying this condition. By adding concept of adding some terms in concept of alpha admissible, Dr. introduced concept of alpha KSP admissible in 2017. Definition is here. In 2018, Peter introduced interpolative kernel type contraction, which is combining idea of interpolative and kernel type contraction. Adding alpha admissible, adding alpha admissible to the left side and side function in the right side of kernel type contraction. Carapita introduced alpha interpolative kernel type contraction in 2019. This is the definition of alpha interpolative kernel type contraction, and these are properties of psi function. Similarly, in the adding to the right side, adding alpha admissible to the right side of setting this type of contraction as well as left side. Adding alpha admissible to the left side, phi function to the right side of setting this type of contraction parameter or introduce alpha setting this type of contraction in 2019. Definition here. Our manager is here. From the motivation by the above work as well as idea of alpha QSP admissible, we redefine alpha QSP interpretive series type contraction and kernel type contraction. By using these two contractions, we prove two new fixed point theory. Alpha KSP interpretive series type contraction theory and accomplishing the politics and the type of some theory. This is the example of a theory. Let us take side alpha is equal to 1 in theory. 1 and 2 we find the following these two quantities. These two quantities are the result of pyramidal details. So our result is extended from the pyramidal detail results. And let us taking about the PHP equal to 1 and sine of t equal to t in our two main result. We find these two quantities. These two quantities are the result of ID details. So our result is generalized from the ID details. This is the application. Our application is defined on theory. Theory 1. Sorry, this theory 2. We define this integral equation as well as we define this matrix B, this matrix T, and also this is the theorem of our application for satisfying those three conditions as well as this contraction. Then this integral equation 7 has solution. That is this D has the fixed point.
Same type of integral, same.
Good afternoon, everyone. Today we are going to present good afternoon once again to everyone. So today I am propagation of grading of equilibrium particles. This is what this is today. So these are the outline of the presentation. First of all, I talk about the modeling of the problem that we have taken, then the logarithm functions, order relations, then vector class and conclusions, and then the review. So this was the problem. This is the problem. First of all, what is the wave? A wave is the disturbance that happens in a media
So it is propagation of energy from one point to another without actually movement in the medium. So here we have considered a two-stream decay rate, which is a horizontally polarized shear wave, and transferring to the media. And there are two medias are considered. One is non-local functioning graded insulated material, and the second one is viscous liquid net. So there is the interface of the solid and the liquid medium. So for the non-local functioning graded insulated material, it is pulled in this direction, determined by the right-hand rule from the x and y axis. So this is the considered structure. The wave propagation is going to follow the anti-plane motion. So for this, the displacement component in two directions is going to be zero, and it will be non-zero only in the third direction, and there will be electric potential in that direction as well. So that is provided in equation number 1. So that's the geometry that is provided here. So for the strain tensor and how is the electric displacement be, that electric is provided in equation number 2. And then electric field components along x, y, z, which can be derived with the equation that is provided in equation number 2. So for the non-local parameter also, for that working equations that are used are provided in equation number 4, where these are the constitutive relations that relate the stress components to the electric displacement and the strain tensor and electric field components. So these are in equation number 4. Here, the elastic constants and the piezoelectric and dielectric constants, they are variable along the x-axis. Delta square denotes the Laplace operator, and here gamma, which ensures the non-locality in the structure, is provided with the relation of product of two parameters, E0 and L. E0 is the material constant that depends on the material, and L is the internal characteristic length, for example, the length of the carbon-carbon bond, and the lattice spacing and Laplace distribution. So this is the equation of motion in piezoelectric medium that we have considered. So cloudy body force is a free charge. The equations are provided in equation number 5. And here, rho is the density of the media. So then, the material properties that are assumed for this structure has positive exponential inhomogeneity along the x-axis that are given in the equation number 6. Here, theta is the material gradient factor, which characterizes the degree of the functional gradientness of the structure. And the values at x is equal to 0 are provided with C44, E15, and kappa. Then, the viscous liquid depth that was drawn there. So the Navier-Stokes equation is used with the neglection of the embroiled inertial term and the pressure gradient that is also ignored, because for the speed propagation during the wave propagation, these two factors have a good role. So the Doherty equation reduces to the equation number 7 that is provided here. So here mu is the dynamic viscous coefficient of the liquid, rho is the mass density of the viscous liquid, and VL is the velocity of the liquid particle in the c direction. So the boundary conditions that we have used for the interfacial effects. So the continuity conditions at the interface x equals to 0 are provided in equation number 8, and the surface of the viscous liquid is taken to be of open boundary, which so that results in equation number 9. And the electrical boundary conditions that we have taken here, so we have considered two cases. One is open circuit condition, and the second one is short circuit condition that are provided in the next subsequent equation. So after the substitution, we have taken the harmonic waveform and substituting them in the Doherty equation. The results are reduced for the open circuit and short circuit conditions separately that are provided in equation number 10 and 11. So for the numerical results and discussions, these are the material constants for piezoelectric aspects that is provided in the table. And for the liquid there, we have used the material parameters for the gasoline that is written there, where the density is taken as 719.7 and viscosity is taken as 0.036. So these are the results that we got from this problem. So here we have discussed the here we have plotted the dispersion relations and plotted velocity profiles for both open and short circuit conditions. And for both the conditions, we will observe that as the value of density is increasing, then the phase velocity is decreasing. So it has a suppressing effect on the phase velocity profiles of the propagating wave. So this is the second result, which is the effect of the coefficient of viscosity. So as the value of viscosity is increasing, the phase velocity of the propagating wave is increasing for both the circuit conditions. Then is the most important factor, that is the non-local factor, which ensures the size dependency, that how it is going to affect the wave propagation
in the phase velocity profiles of the propagating wave for both the circuit conditions. Then the last one is the effect of the integral gradient coefficient, that this factor is responsible for the inhomogeneity in the media. So here we can observe that as the value of this parameter increases, then for both the circuit conditions, the phase velocity profiles also increases. So these are the conclusions that I have already explained with the results. Thank you. That happens when there is love and confidence. That's right. That's what is always to use like the landscape. Life experience to extension all of your insightful discussions. Now, this is a frame for from 5 p.m. So please make sure to be back in your small in your seats by then to experience the culture and tradition of India. I thank all of you again for attending this session.
Can you talk photographs of I actually noticed sort of तुमको एक रिप्लेसमेंट डाल दे सकते कौन सा इसको बोल Oh, no. Yeah, that will be sending in that.